Buenos días a todos, muchas gracias por la paciencia. Como siempre, estamos partiendo a la hora en punto chilena. Y estamos esperando a nuestro primer presentador que viene un poquito atrasado. Así es que vamos a partir con una pequeña introducción a lo que se viene. Primero, bienvenidos a este seminario, la calidad del aire como un compromiso compartido. Esto lo llevo organizando desde quizás varios años, tratando de convencer a grandes expertos mundiales de que vengan a hacer una visita a Chile para poder motivar un poco a la industria, a la academia y también al sector público a seguir avanzando en un tema que es muy relevante para nosotros, mucho más ahora que se viene la nueva reglamentación térmica. Hemos avanzado como país en varios sectores y en varias propiedades de la edificación, sobre todo en la eficiencia energética, pero eso puede conllevar o podría empezar a tener muchísimas consecuencias en otros aspectos que a lo mejor no estamos visualizando. Y cuando he compartido con estos expertos durante los últimos 7 años, las conversaciones van un poco en eso, en tratar de compararnos, que al final da un poco de ganas de que ellos pudiesen además venir a dar su perspectiva de cómo ellos han visto a lo largo de su vida para algunos y también en su carrera, cómo ha avanzado la industria, cuáles han sido las brechas, cuáles han sido las mayores trabas. Y de repente les pregunto si tuvieran que volver a hacerlo, ¿cómo lo harían? Toda esa experiencia y nuevos conocimientos y la forma de haberlo hecho, yo creo que nos va a servir mucho para nutrirnos como industria y como sector público, privado y academia, para poder hacer las cosas bien de una vez y empezar a visualizar posibles consecuencias de no hacerlo correctamente o de no tomar las precauciones desde el minuto uno. Tenemos una tremenda oportunidad de empezar a practicar lo que se ha hecho internacionalmente y aprovecharnos de la experiencia extranjera. Nuestro primer speaker, Max Sherman, recuerdo que cuando estaba buscando mi doctorado le iba a escribir, menos mal que no escribí un correo, porque si no, él no estaría acá y la historia sería muy distinta, pero lo conocí haciendo mi doctorado y fue uno de mis grandes mentores también, ha sido y está siendo también un gran guía en mi proceso profesional y académico. Tengo la suerte además de que está jubilado y que tiene más tiempo para viajar y hacer un viaje enorme desde California. Ha sido uno de los pioneros en el desarrollo de la hermeticidad y cómo medir hermeticidad en viviendas y edificios. Y también ha visto el desarrollo de la actual reglamentación de ventilación que estamos adoptando, la HRAE 62.2, y por lo tanto nos va a contar un poco la historia, el pasado, el presente y el futuro que viene respecto a la ventilación, para que nosotros ya nos pongamos en contexto de cómo ha sido el desarrollo desde el día 1, cuáles han sido las distintas conversaciones y discusiones respecto a este parámetro y después cómo él visualiza el futuro. A Valérie Le Prince de Cerema, Francia, también la conozco hace unos 7, 5 años quizás. Es una excelente profesional, muy inteligente y ella además está muy en contacto con la industria. Ella trabaja en control, en entregar también consejos a la industria respecto a cómo llevar a cabo y cumplir con las reglamentaciones no tanto nacionales sino también a nivel europeo. Por lo tanto, ella también tiene una visión ya europea y de cómo podríamos nosotros traducir literalmente estas reglamentaciones, estos estándares a nivel nacional según el contexto. Así es que está muy interesada también de conocer las condiciones en que nosotros operamos nuestros edificios, cuáles son las formas de cumplimiento que podríamos nosotros empezar a exigir y cómo seguir avanzando en este desarrollo. Y finalmente a Benjamin Jones lo conozco también hace ya 10 años o quizás un poco más. Lo conozco también desde mi doctorado. Es un experto en modelamiento de viviendas, en la física de la edificación y durante la pandemia tomó la oportunidad de estudiar el control de patógenos en edificios y cómo poder reducir el riesgo de infección del COVID durante estos años. En sus países, en sus respectivos países, en Inglaterra, Francia y Estados Unidos, tienen un nivel de desarrollo que es envidiable. Y yo creo que va a ser muy enriquecedor para todos nosotros escuchar sus versiones, sus interpretaciones y también su forma de aplicar estas normativas y estos nuevos desarrollos. Así que para abrir la discusión, les quiero presentar también a nuestros sponsors. Esto no sería posible sin el financiamiento de un fondo de iniciación del que yo soy primera investigadora. Pero también tenemos el apoyo de Azrae Chile y Azrae Mundo, que trajo a Max a Chile. Eh, de CONUC también está como sponsor y CIPIX, de la universidad, ambas de la Universidad Católica. Así que para partir invito a René. René, ¿dónde estás? No te veo. René nos va a hacer una introducción a lo que es Azrae Chile en este minuto y cómo estamos involucrados nosotros ahora en la reglamentación térmica. Así es que un gran aplauso y que disfruten.
¿Cómo cambia? Hola, buenos días. Soy René González, el presidente electo del capítulo chileno de Azrae. Es un gusto para mí estar acá y como Azrae Chile es un honor poder patrocinar este tipo de eventos que van en línea con lo que nosotros buscamos como asociación. Ahora, para comenzar, me gustaría darle una pequeña introducción de lo que es ACHRAE, la Asociación Americana de Ingenieros en Calefacción, Refrigeración, Aire Acondicionado. Tenemos alrededor de 57.000 miembros alrededor del mundo, presencia en 50 países. Nos dedicamos a publicar estándar, guías. Somos voluntarios en una asociación ad honorem. Me gustaría mostrarles esta pequeña infografía que detalla un poco lo que hacemos a nivel mundial. Tenemos 21 estándares publicados, 41 proyectos activos. Esta infografía es un poquito antigua, así que hay algunos números que son un poco superiores. En la página web de ACHRAE se pueden encontrar con una cantidad de documentación que es un poco chocante al principio, pero a medida que uno se va relacionando con el tema o que tiene claro qué quiere buscar, es mucho más fácil encontrar este tipo de información. ACHRAE funciona como una asociación de voluntarios, no hay miembros de empresas, son profesionales que están involucrados con diferentes rubros de la sustentabilidad, de la ingeniería, la arquitectura, la construcción, la evaluación energética. Y bueno, la membresía tiene un costo. De cierta forma como ACHRAE se financia para generar los proyectos de investigación, para poder publicar los estándares. En este caso, en este mismo evento, tenemos como invitado a Mac Sherman, que él es un lector distinguido de ACHRAE. Son los DL o lectores distinguidos. Son personas que han demostrado con los años que tienen un conocimiento acabado en ciertos temas, trabajo en comité, y ACHRAE los pone a disposición del mundo para transferir este conocimiento a diferentes lugares del mundo. ACHRAE, como les planteaba, es una asociación global, la cual se divide en 15 regiones alrededor del mundo. Nosotros correspondemos a la región 12, que es Latinoamérica más el sur de Florida, y somos 16 capítulos al interior de la región. Ahí están los 16 capítulos, nosotros somos el número 196. Ahí está Chile. Nosotros, este año es súper importante para nosotros porque cumplimos 10 años de formación. HRAE a nivel global tiene más de 130 años, nosotros apenas tenemos 10, pero eso no significa que estemos atrasados en la adopción de normativas. Chile históricamente sí se ha basado en estándar de HRAE para su legislación y para su normativa. ¿Qué hacemos nosotros? Tenemos 10 comités, que luego voy a profundizar en eso. Promovemos las buenas prácticas, lo organizan los mismos miembros voluntarios. En Chile somos actualmente 48 miembros. Somos un capítulo muy pequeño en comparación con otros países, pero no por eso hemos dejado de hacer cosas. Como les comentaba, estos 10 años no siempre han sido fáciles. O sea, nosotros actualmente somos un capítulo que está ciertamente consolidado, hemos sido reconocidos a nivel regional, pero ha tenido las dificultades de que una fundación sin fines de lucro, donde a veces el financiamiento es difícil, donde la temática es complicada. A mí no me gusta hablar como que la pandemia fue algo beneficioso. Pero si buscamos el lado positivo de las cosas, dejó en evidencia que la calidad de aire interior en las edificaciones era algo de real importancia. No sería ilógico pensar que en el futuro vuelva a ocurrir otra pandemia y nosotros debemos estar preparados, porque no se puede detener el mundo, no podemos vivir con el miedo de seguir encerrados en nuestras casas. A veces existe la posibilidad de que quizás nuestros entornos, nuestras edificaciones, incluso sean más seguras. HRAE no solamente está compuesto por ingenieros. Contamos con miembros que son ingenieros en medio ambiente, ingenieros químicos, arquitectos, constructores. Nosotros quizá en Chile estamos un poco al debe en esta apertura del rubro, pero lo buscamos activamente. Queremos tener más miembros que vengan de otras líneas profesionales, porque precisamente esta correlación de conocimiento, este compartimiento, este networking, nos fortalece en lo que es nuestro trabajo local y en nuestro trabajo internacional. Lo que les comentaba, HRAE tiene este funcionamiento que funciona, existe una asociación global, la cual también tiene una fundación, está dividida en estas 15 regiones, en donde existe conferencias regionales de capítulos. Tiene por otro lado comités técnicos. Constanza ya le hablaba de que Max presidía uno de los comités técnicos del 62.2. Comités técnicos calidad de aire interior habitacional, calidad de aire en instituciones médicas, calidad de aire en edificios, 90.1 que habla acerca de la eficiencia del equipamiento, estándar de cómo se mide aire, cómo se mide temperatura, cómo se mide agua, guías de diseño para hospitales, oficinas, centros de educación, manuales de uso de estos estándares, cartas de posicionamiento, que a veces no son tan conocidas como los estándares, pero las cartas de posicionamiento de HRAE únicamente son publicadas cuando existe antecedentes completamente fidedignos de que son reales y son beneficiosos para el estudio. Nosotros estamos formados por un directorio, más de 10 comités. Hay comités que son más antiguos, como los de transferencia tecnológica. asuntos gubernamentales. Nuestro trabajo y lo que nos enorgullece es que hemos logrado trabajar en los comités técnicos de la normativa del Instituto Nacional de Normalización. Trabajamos en la 3309, en la 3308, que son de calidad de aire interior, tanto en edificaciones como en edificios habitacionales. En la familia de normas que tienen que ver con la eficiencia energética de la ISO 50001, normas de instalaciones. Hemos tenido reuniones con diferentes ministerios, siempre impulsando que Chile pueda contar con más y mejores normas que tengan que ver con la sustentabilidad y el uso de la energía. Nuestro desafío, uno está tachado porque buscábamos que esta normativa de aire estuviera en la UC. Afortunadamente, desde noviembre de este año se vuelve oficial. ¿Qué nos queda? Nos falta trabajar en calidad de aire hospitalaria. Tenemos que trabajar en lo que tiene que ver con normas de incendios en ventilación y el uso del aire. Y, ¿por qué no también avanzar en que Chile tenga normativa acerca de comisionamiento en lo que es el desarrollo de edificaciones? Algunas fotos de nuestras participaciones, los grandes logros que hemos tenido, yo algunos me adelanté, también congresos técnicos, conjunto con la Cámara Chilena de Refrigeración. El año pasado desarrollamos todas las charlas técnicas que tuvieron que ver de la Feria Frío-Calor. Hemos obtenido reconocimiento a nivel mundial como un premio de tecnología, en donde pudimos demostrar que incluso de países como Chile tenemos reconocimiento a niveles globales. No estamos tan mal después de todo. Algunos de los premios que ha tenido el capítulo: premios al capítulo y al comité de asuntos gubernamentales, por lo mismo que les comentaba acerca del trabajo normativo en Chile. Un reconocimiento a Hermes Silva con su empresa por el Technology Awards. Nuestras metas. Bueno, nosotros queremos volvernos un referente y este tipo de actividades nos permite poner nuestros conocimientos al servicio de la comunidad, del que esté interesado. HRAE, una de las cosas que a mí me ha sorprendido como asociación es la buena voluntad de sus miembros. O sea, que siempre conocer a una persona en donde uno pueda preguntar cuáles son las dudas, de si desconoce algo, al menos conocer a una persona que sí conoce el tema. Eso realmente se vuelve gratificante, porque no quiero decir como una familia, porque es como un cliché, pero realmente es el tema del conocimiento se comparte sin interés alguno. Bueno, es una foto no tan reciente, pero muestra cuál es el directorio del capítulo. Y los invito a que visiten nuestra página web. Y sería eso. Muchas gracias.
Gracias, René, presidente electo de HRAE Chile. Ahora quiero invitar a Julio Maturana. Él es el jefe de división de energías sostenibles del Ministerio de Energía y presidente del Consejo Directivo de la Comisión de Energía Nuclear, que tiene unas palabras para nosotros.
¿Qué tal? Hola, buenos días a todos y todas. Bueno, estoy acá en reemplazo del subsecretario de Energía que me pidió estar acá hoy día. Él venía a dar unas palabras de inicio a este seminario. Lamentablemente él no pudo asistir. tuvo algunos compromisos de emergencia, tiene que también viajar hoy día, así que me pidió estar acá. Bueno, yo soy Julio Maturana, tal como dijeron, soy el jefe de la División de Energías Sostenibles, también cumplo otros roles, efectivamente estoy en la Comisión Chilena de Energía Nuclear, pero además también estoy en la Agencia de Sostenibilidad Energética, en donde precisamente vemos este tipo de temas. La eficiencia energética es uno de nuestros objetivos. Y precisamente en la División de Energías Sostenibles, una de nuestras unidades es la unidad de edificación y ciudades, que dentro de todas las cosas que hace, el tema de la eficiencia energética es uno de los principales objetivos que tenemos, no solamente dentro de esta unidad de la división, sino que dentro del ministerio. Hace varios años atrás, uno muchas veces asume esto como... Voy a hablar un poco más lento porque es verdad que estamos con traducción simultánea. I'm sorry. Uno asume esto como parte de algo como lo que hay que hacer, como algo, como los países deben hacer este tipo de cosas. Sin embargo, hace pocos años nosotros como país tenemos una ley de eficiencia energética. Es algo relativamente reciente. Y creo que una de las cosas valorables que tiene nuestro país hoy día respecto a este tema, la eficiencia energética, es que durante mucho tiempo nos estuvimos poniendo de acuerdo entre diferentes sectores, la industria, el sector público, el sector privado, para llegar a un consenso respecto a diferentes cosas. En el sector automotriz, en el sector de la construcción, en el sector también de las energías, hasta llegar a un consenso respecto a una ley de eficiencia energética que nos permitiera avanzar en los diferentes ámbitos, no solamente en la reducción de emisiones, que siempre ese es el objetivo final, sino que también en mejorar la calidad de vida de las personas a través de, en este caso, el confort térmico. En Chile tenemos una brecha muy importante respecto a los temas de calefacción, o como decimos coloquialmente, el calor y frío. Probablemente uno de los grandes o una de las grandes brechas energéticas que hoy día tenemos en el país a escala de las personas no tiene tanto que ver con la matriz energética como tal. El ciudadano de a pie, si bien es cierto, yo creo que le impacta mucho que hoy día la energía no sea las termoeléctricas, sino que sea a través del sol, eólica, etc. Lo que más le impacta es esa persona que está hoy día en Puerto Montt, hacen 3 grados y su calefacción es a leña y está viviendo la polución de la leña, las ciudades están contaminadas y eso afecta directamente su salud, afecta directamente en cuánto tiempo puede estar, ¿cierto?, fuera de su hogar, impacta en su bolsillo en términos monetarios, en cuánto gasta en calefacción, impacta también en cómo convive, ¿cierto?, con las otras personas en los lugares en los que está, digamos, dentro de su ciudad, si es que un lugar es caliente, es frío, etc. Esa es la gran brecha que hoy día tenemos en términos energéticos, y eso se da en gran parte del sur del país y también en algunos sectores del norte del país. Las brechas térmicas o las diferencias térmicas, ¿cierto?, en algunas partes del norte son súper importantes. Entonces, cuando hablamos de eficiencia energética, en este caso en lo residencial, tenemos mucho por avanzar. Y aunque a veces es muy técnico hablar de la norma chilena, número tanto, etcétera, es una cuestión que impacta directamente en la calidad de vida de las personas. Cuando por fin este tipo de normas se transforman en una cuestión que sí o sí tiene que estar, o sí está por ley, o sí la construcción las tiene que implementar al momento de hacer una vivienda nueva, la calidad de vida de las personas cambia completamente. Afecta su bolsillo, afecta también la forma en cómo se relaciona con los demás y además que son viviendas mucho más duraderas. Tenemos todavía esta brecha, como les comentaba, de todas estas viviendas que todavía tienen una calidad que son mucho menor a lo que hoy día tenemos como normativa respecto a viviendas. Y por otro lado, tenemos también el tema de los edificios. Hay varias certificaciones hoy día relacionadas con eficiencia energética, de precisamente los temas de calor y frío, y tenemos también ahí una brecha importante que avanzar. Está el tema hospitalario. No solamente pensemos en los grandes, digamos, hospitales que efectivamente tienen infraestructura con calderas, por ejemplo, tenemos hartos espacios como para hacer innovación tecnológica. También pensemos en la pequeña infraestructura hospitalaria, en los CEFAM, en los COSAM, en esos lugares en donde las personas que están en sus casas hoy día pasando frío, tienen que ir a tomar una primera atención de salud a pasar frío nuevamente. Es ahí en donde está el desafío. Tenemos también desafíos en la infraestructura, por ejemplo, de escuelas. Nosotros en el ministerio este año estos últimos años hicimos un gran esfuerzo en hacer un programa de acondicionamiento térmico de escuelas, en donde elevamos el estándar del acondicionamiento térmico de varias escuelas en el país, que lo sentíamos no solamente como como simplemente hacer un programa de mejoramiento, sino que también lo sentíamos como una obligación básica con los niños y niñas del país, porque habían escuelas en donde la calefacción era a través de salamandras. No sé cómo van a traducir salamandras, la verdad, pero es lo más parecido a tener unas maderas quemándose dentro de una sala en un espacio cerrado para poder calefaccionarlo con todo lo que es, digamos, el CO2 y la polución en el mismo lugar en donde se tiene clases. Entonces, hay toda una brecha, por ejemplo, como les comentaba, en lo que tiene que ver con la infraestructura hospitalaria, en lo que tiene que ver con la infraestructura escolar, en lo que tiene que ver también con la infraestructura pública, que tenemos que avanzar en esos espacios. Por lo tanto, cuando conversamos de eficiencia energética, de calor y frío en la edificación, tenemos todavía muchas cosas en las que avanzar, muchas cosas en las que trabajar también, ponernos de acuerdo. Se han hecho muchos avances en estos últimos años. Y por eso les comentaba al principio que, aunque pareciera que esto es como algo que debiese haber estado siempre y que tenía que haber sucedido, hasta hace pocos años no lo teníamos. Y es muy bueno que ahora lo tengamos y es muy bueno que estemos avanzando en obtener más cosas y en avanzar más en eficiencia energética en edificaciones, porque sin duda ese va a ser el camino que nos va a permitir, por un lado, disminuir las emisiones, que es lo que todos queremos, pero además nos va a permitir un mejor confort térmico para las personas, un mejor también confort térmico para las instituciones, pero además también nos va a permitir mejorar la calidad de vida de cada una de las personas. Así que bueno, espero que disfrutemos este seminario, tanto los que están acá como también los que nos están mirando online, y que podamos seguir cooperando entre la academia, el sector público y también el sector privado. Muchas gracias.
Hola de nuevo. No soy así de alta, por supuesto. En nuestra escuela tuvieron la gentileza de hacerme un pisito para yo poder verme mejor. Bien, yo quiero contarles un poco sobre lo que hemos hecho los últimos 3 años en el marco del proyecto Fondos de Iniciación, en el que soy yo investigadora principal, pero también cuento con la colaboración de varios expertos. Muchos de los que están acá también han aportado bastante al desarrollo e interpretación de los resultados de este. Bien, me robé el título del seminario, tuve la patudez de hacerlo, porque quiero que en el fondo tengamos esta discusión de cuáles son los parámetros que también están involucrados en la calidad del aire y que de repente hacen de enemigos y de contraparte para poder llegar a un estándar deseable. Nosotros en Chile hemos avanzado bastante en temas de eficiencia energética en los últimos 20 años, gracias a gente que se ha ido a capacitar al exterior y también dentro del país, y que tienen experiencia tanto en la academia como en la industria. Pero a veces dejamos de lado algunas consecuencias indeseadas que podrían tener consecuencias en la salud de nuestra población y que a lo mejor estamos no solo viéndolas ahora como enfermedades crónicas, sino que también vamos a ir viéndolas como enfermedades agudas, sino también vamos a verla en algún minuto como enfermedades crónicas. Y la exposición a contaminantes no es algo trivial, es parte de un sistema en el que están involucrados bastantes otras variables y otros efectos. Y por lo tanto tenemos que pensar que no solo las viviendas tienen mucha variabilidad en Chile, tanto en sistemas constructivos como también los usuarios. Tenemos usuarios que ocupan las viviendas de forma distinta y también los ocupantes de edificios públicos hacen uso de ellos de forma variada. Por lo tanto tenemos que tener en cuenta esa variabilidad tanto del ocupante, del ambiente, que tenemos muchos de los climas que hay en el mundo, los tenemos aquí en Chile. Somos un laboratorio natural muy valioso, del que yo me regocijé durante mi doctorado porque pude aplicar muchas de las cosas que se están haciendo en otros países, aquí en alguna de las ciudades nacionales. Así es que ocupar esto como también una forma de laboratorio es algo muy importante, pero tenemos que empezar a buscar información. Y es por eso que creé este proyecto Fondesit de Iniciación, que es uno de varios que se están haciendo también en este minuto a lo largo del país. Este tiene el foco en Santiago por un tema también económico y práctico. Yo lo postulé justo en época de pandemia, por lo tanto ir a visitar otras ciudades era prácticamente imposible, lo iba a hacer un poco viable. Por lo tanto me centré en Santiago y empezamos a monitorear viviendas que están repartidas en el Gran Santiago, y en realidad nos damos cuenta de que el problema no solo es cómo ocupamos nuestras viviendas, qué actividades estamos haciendo que tienen que ver con la persona, sino también cómo nosotros construimos nuestros edificios, cómo nosotros los equipamos finalmente con a lo mejor equipamiento que el usuario no sabe ocupar. Y que cuando uno le va a preguntar al ocupante, al propietario o al usuario principal, a veces no saben cómo utilizarlo y empiezan entonces con estas patologías tanto del edificio como de las personas. Tenemos una mezcla de contaminantes, a veces nosotros pensamos que la contaminación del aire viene solo de afuera, pero en realidad esto es introducido a través de infiltraciones y exfiltraciones por la envolvente. Tenemos también objetos mobiliario y también actividades que generan contaminantes, que son fuentes de contaminación importantes y que a veces no son suficientemente ventiladas o ventiladas correctamente, y por lo tanto la exposición se hace prolongada. Tenemos también algunas mejoras que nosotros pensamos que le estamos haciendo a nuestras viviendas. De repente pensamos en ese olor a vivienda nueva como algo exquisito. Bueno, a veces las noticias no son tan positivas como esas y estamos expuestos a contaminantes que está comprobado y tenemos evidencia científica ya de que pueden causar enfermedades crónicas. Así que tener eso en cuenta cuando nosotros tenemos esta batalla, ¿cierto?, de disminuir la energía consumida con la salud. Hay que balancearlo con el efecto en la salud de los ocupantes, tanto de las personas vulnerables como no tan vulnerables que están viviendo en ella. El confort térmico, que a veces se prioriza, ¿cierto? Nosotros les voy a mostrar más adelante algunos resultados nacionales, pero en realidad nos destacamos por tener viviendas frías, al menos en el centro y sur del país, y estamos acostumbrados a eso. Las proyecciones y simulaciones pueden ser a veces sobreestimadas si nosotros ponemos como por defecto condiciones que no son reales y por lo tanto podrían darnos resultados distintos. Y finalmente sabemos que condiciones hidrotérmicas en un edificio puede tener consecuencias indeseadas también en los materiales, en su durabilidad y por lo tanto la sostenibilidad en el tiempo. Entonces, para darles algunos parámetros que hemos medido, el confort térmico en nuestras viviendas hemos aprendido bastante. Hay harto que aprender aún. Nosotros somos un atado de nervios, digo yo. El cuerpo está constantemente sintiendo estímulos y generando respuestas. A veces son conscientes, a veces son inconscientes. Y tenemos que tener eso en cuenta al momento de diseñar y operar nuestros edificios. A veces priorizamos el estar calientitos con la ventilación y eso trae sus consecuencias también indeseadas. ¿Qué ha pasado en un año, el 2023, fuera de la pandemia? Ya había terminado. Empezamos a medir condiciones hidrotérmicas. Los limitantes de trabajar con edificios como objetos de investigación es que no nos podemos meter mucho con el ocupante, por lo tanto, estas son las condiciones interiores de la vivienda durante todo el año. Solo un 54%, como ahí se ve en el área roja y azul, es cuando el ocupante dentro de esas viviendas estaría en confort térmico. O sea, tenemos 50 y 50% de probabilidad de estar en confort térmico en nuestras viviendas. Las condiciones extremas que se presentan tanto en épocas de invierno como en verano salen de esta área de confort. Y tenemos que tener eso en consideración al momento de diseñar y operar nuestros edificios. Cómo le enseñamos o exponemos a la información, como podríamos decir más políticamente correcta, exponer a la información al usuario de cómo utilizar su vivienda para estar en mejor control. Si nosotros nos ponemos ahora a medir contaminación interior en nuestras viviendas, nosotros nos damos cuenta de forma positiva, pero en realidad tenemos mucho que mejorar igual, de que existe una gran variabilidad entre viviendas y dentro de la vivienda. Estamos, en general, las estadísticas dicen que estamos mejor que el promedio mundial. Sin embargo, estos valores debiesen llegar a cero. No hay un límite inferior para la exposición a material particulado que tenga algún efecto en la salud. Y por lo tanto, si nosotros, claro, vemos el vaso medio lleno, estamos en promedio. En Santiago, la mediana está bajo la mediana mundial, pero tenemos que seguir mejorando. Estas son condiciones solamente interiores y tiene que ver mucho con la ventilación. Nosotros a lo mejor no sabemos ventilar. La siguiente expositora, Valerie, nos va a hablar de qué es ventilar. A veces le preguntamos a las personas que ocupan las viviendas, ¿usted ventila? Y nos dicen sí. ¿Cómo ventila? Abro la ventana en la mañana. Y con eso se quedan. Y con eso se quedan tranquilos. Valeria nos va a decir, eso no es ventilar. Eso está aireando la vivienda. Y por lo tanto tenemos que ocupar el conocimiento tanto de las personas como de la vivienda y su entorno para poder diseñar correctamente tasas de ventilación mínima que permitan mantener un aire aceptable interior. Por lo tanto, no solo ventilamos para poder reducir las concentraciones de contaminantes nocivos, sino también para mejorar el confort térmico. Algunas viviendas en verano se sobrecalientan y el ocupante tendrá que decidir si abre o no la ventana. ¿Será la mejor opción? Tendremos que seguir mejorando en esa estación del año. Y el confort térmico en invierno también. ¿Qué hacemos con ello? ¿Abrimos ventanas si es que afuera está contaminado y más contaminado que adentro? ¿Cómo saberlo? ¿Cómo tomar esa decisión? No es trivial. Y hay que exponer al usuario a esa información y a esa toma de decisiones correctas. Luego el confort respiratorio a veces nosotros lo pasamos de lado porque a no ser que olamos algo que nos incomode, no vamos a ventilar o no vamos a aumentar las tasas de ventilación. No todos los contaminantes tienen olores, muchos de ellos no lo tienen o se los agregamos en forma artificial, pero tenemos que también tener conciencia de que tenemos que implementar una tasa de ventilación mínima y luego incrementarla si es que nosotros sabemos que tenemos fuentes de contaminación extras. Y finalmente tenemos que mejorar las condiciones interiores para mejorar la durabilidad de las viviendas. Y no solo en el confort térmico, sino también en la contaminación. ¿Cuánto? Ya sabemos cuánto. Tenemos unas guías normativas ahora que nos van a orientar en cómo calcular las tasas de ventilación en función, ya sea si sabemos de qué tamaño es la vivienda, cuántas personas viven en ella, cuántas personas duermen en ella, qué tamaño tienen los dormitorios, serán ventilados en forma eficiente para un buen dormir, un buen descansar, o van a estar superando las tasas, las concentraciones de contaminantes y van a empezar a tener sus consecuencias. Estamos entonces adaptando una normativa más actualizada, pero tenemos que también ir pensando en equipar a nuestras viviendas si es necesario. Y este es el dilema. El dilema es que si yo no ventilo lo suficiente, claro, me voy a ahorrar energía quizás, pero en desmedro de la calidad del aire y probablemente de la salud de sus ocupantes. Y uno de los mensajes que quería entregarles es que hay muchos edificios que no están siendo ventilados correctamente o que no sabemos cómo se están ventilando, no tienen las tasas de ventilación mínima. Y este gráfico, si ustedes ven la primera curva que baja, indica la primera zona de grandes mejoras. Nosotros no tenemos que tener necesariamente, a no ser que tengamos alguna razón muy justificada, de sobreventilar. En épocas de pandemia probablemente nos va a contar Benjamin Jones qué podemos hacer en épocas de pandemia para reducir el riesgo de infección, pero tenemos una gran área de mejora, al menos empezar a ventilar lo necesario, aquellos edificios y no solo viviendas que no están siendo ventilados. Y eso nos dimos cuenta gracias a un proyecto del Instituto de Suceso, liderado también, de contraparte tuvimos al Instituto de Salud Laboral, en donde nos pidieron estudiar los edificios de trabajo ocupacionales, y les fuimos a preguntar, bueno, ¿y usted cuánto ventila? ¿Cuánto es la tasa de ventilación que provee a sus trabajadores? Y no sabían. Llegamos a una tasa de respuesta de un 1%, información que terminó siendo inútil porque la gente no sabe cuánto están ventilando, cuáles son las tasas de ventilación por persona, caudales de ventilación para los distintos recintos y por lo tanto las formas de mejorar también son mucho más difíciles de implementar y de recomendar. Y luego tenemos una zona en donde quizás la ventilación sería excesiva. Ponerse también sobreexigentes y empezar a ocupar quizás más energía de la necesaria también es el límite superior, ¿cierto? En este sentido. Y tenemos con eso estas exigencias energéticas en donde tenemos que ponerle también ojo. Y los recintos de trabajo también tienen que ser un espacio en donde el ocupante se sienta protegido, pero también le entregue confort al usuario para poder hacer su trabajo de forma más productiva y confortable. ¿Cómo operan nuestros edificios? Como les contaba, nuestros edificios, al menos los edificios públicos, no sabemos. Tenemos información muy limitada también de las tasas de ventilación en viviendas. Hay ensayos que se están empezando a hacer o que se han hecho durante los últimos 10 años, pero que son muy poquitos. No nos sirve todavía para tomar buenas decisiones o basadas al menos en evidencia. ¿Y cómo mejorar? Valerie Leprince nos va a contar cómo podemos empezar a hacerlo. Porque podríamos tener consecuencias en nuestra salud, sobre todo la salud respiratoria de nuestros ocupantes y sobre todo de la población vulnerable, la gente adulto mayor, los niños chicos que se quedan todo el día en la casa o están todo el día en el colegio o los profesores, ¿cierto? La gente que trabaja necesita sentirse protegido. Por lo tanto, la buena noticia es que Chile está avanzando sobre eso. La regulación actual no era suficiente o no estaba siendo exigida tan fuertemente, pero estamos mejorando. Y las normas nuevas nos van a entregar una guía bastante completa de cómo hacerlo, cuánto hacerlo y cómo controlarlo también. Estas tienen que tener como objetivo, como les decía anteriormente, balancear las necesidades de bienestar, salud, eficiencia energética o uso de la energía y confort del usuario. Y después nos hicimos una pregunta: ¿qué pasa con la contaminación exterior versus la interior? ¿Estaremos más seguros dentro de nuestras viviendas o fuera de nuestras viviendas? Nosotros siempre tenemos la apertura a estas presentaciones con la frase cliché, ¿cierto? De que a veces nosotros en nuestra disciplina, de que en el interior podríamos estar en peores condiciones que en el exterior y es por eso que tenemos que ventilar. Bueno, la pregunta era entonces, ¿cómo lo estamos haciendo acá en Chile? Y en realidad la línea que está ahí punteada indica iguales condiciones, es decir, da lo mismo si estoy dentro o fuera o tengo una vivienda muy, muy ventilada en que las condiciones exteriores son las mismas que tengo adentro. Sobre esa línea punteada tenemos las condiciones en donde la contaminación es peor fuera. En Santiago, insisto, durante todo el año le gana a las condiciones interiores. He tenido que cambiar mi discurso, al menos para cuando presento el caso de estudio en el contexto chileno, en donde se da que la mayoría no implica que la persona esté en esa casa, pero que la mayoría del tiempo las condiciones están peores más afuera que adentro. Y esto puede ser muy común en en gran parte del tiempo. Y aquí estamos peor dentro. O sea, tenemos que de repente pensar, lo puse al revés, me acabo de dar cuenta. Las condiciones están peor dentro que afuera. Perdón, son mayores. Pero hemos ido avanzando. Después nos hicimos la pregunta, bueno, hemos mejorado nuestras viviendas, ¿cierto? La hermeticidad, la aislación, las condiciones de ventilación y el tiempo, ¿cierto? Según el año en que fueron construidas las viviendas, ¿estamos mejorando? Y se ha visto una tendencia, no sé si se alcanza a apreciar, pero al menos en exposición de material particulado grueso y fino, estamos mejorando en el tiempo. Las mejores condiciones las están teniendo las viviendas que fueron construidas luego de la segunda reglamentación térmica. Por lo tanto, quizás las buenas noticias es que vamos a seguir mejorando aún más, haciendo nuestras viviendas más herméticas, pero tenemos que controlar, tenemos que recoger evidencia. No es tan sencillo como prescribir algo, alguna solución, construirla lo mejor que podamos y luego olvidarnos de esa condición. Tenemos que empezar a controlar y empezar también a registrar. Por lo tanto, el llamado y mi segundo mensaje es a seguir teniendo este tipo de discusión, nuevas iniciativas que busquen registrar las condiciones interiores en donde cómo están viviendo las personas, cómo se sienten, hay bienestar, hay confort, se están enfermando. Tenemos que trabajar con distintas disciplinas, con distintos expertos que nos entreguen esos inputs y esa información. Por lo tanto, el llamado es a generar estos nuevos comisionamientos, ¿cierto? Generar encuestas y que nosotros ya tenemos. Somos ricos en datos, pero a veces no lo sabemos leer en forma conjunta y hacer cruces de información que nos puedan dar una mayor información. La CACEN, la ENUT, la Encuesta Nacional del Uso del Tiempo, nos dicen dónde están los chilenos durante el día, qué hacen, dónde viven, dónde están. Y eso nos entrega información para poder complementar con el diseño de nuestros edificios. El censo también nos entrega información de condiciones de construcción. La CACEN, ¿en qué condiciones están? ¿Hay hacinamiento? ¿Hay déficit habitacional, cualitativo, cuantitativo? ¿Se están enfermando esa gente? ¿Qué enfermedades tienen más comunes? Y finalmente todo eso nos sirve para reducir lo desconocido. Así que con eso espero haberles dado un pequeño contexto de las condiciones de habitabilidad en Chile. Y ahora quiero presentar a nuestro primer speaker, Max Sherman, que nos va a contar un poco cómo ha sido la evolución en otros países, especialmente en Estados Unidos. Él es el pionero y a lo mejor lo van a seguir escuchando porque es una de las personas que ha desarrollado el ensayo de hermeticidad en viviendas, el Blower Door Test. Gracias a él lo tenemos también. Así es que muy orgullosa de tenerlo acá en Chile y espero que disfruten. Muchas gracias.
Thank you, Connie, and I hope you can all hear me and understand, so I will try to speak slowly, and I apologize in advance because I probably won't. So as you've heard, I'm an ASHRAE Distinguished Lecturer. ASHRAE has asked me to, or arranged for me to come here to speak to you and to help you. Distinguished Lecturer is one of the things that ASHRAE likes to do to help people in the various chapters get the technology. There are over 100 distinguished lecturers talking on about 300 different subjects, and we go around to chapters and do it. So these are the things which we're always asked to tell you, to keep your phones quiet, et cetera, et cetera. So ASHRAE exists and is effective because of volunteers. Volunteers both at the national and at the chapter level. So it's what keeps our industry moving. It's what helps ASHRAE progress. So I encourage any of you who are not ASHRAE members to consider joining. There's a small ASHRAE and very powerful ASHRAE chapter here in Santiago. I hope you can grow it. And ASHRAE has bequeathed copies of 3 standards here for the chapter's use. So these are the 3 standards I'm going to talk about a little bit today: 62.1, 62.2, those are the 2 ventilation ones, and 241, which is the infection control one, which I won't talk too much about, but the chapter has a copy of those. This is what I looked like when I first started being a distinguished lecturer, so it's been quite a while. I have a ASHRAE career. I've been chair of 62.2. I've been on these committees. I'm vice chair of environmental health. I'm vice chair of the 241 committee. I've been on the board. So I have been around ASHRAE quite a bit. What I'd like to do today is give you a broad view, a historical view, past, present, and future, of ventilation and indoor air quality. So I'm going to start with talking about the history of ventilation, way back when. And then we're going to move on to a little bit of science. Then we're going to talk a little bit about standards. We're going to talk about carbon dioxide, because that seems to be a very popular thing for people to worry about these days. And then I'm going to move on to what essentially is the future, which is where 62.2 and eventually 62.1 will go, which is harm-based standards. So this is a little bit of a quiz for you all. So when do you think ventilation was first mastered? Who were the masters of ventilation? Think to yourself a little bit of what that might be. What's the answer to this question? What were the earliest techniques? How did they work? And all that sort of thing. I'll give you a moment to think about it before I give you the answer. And I'm guessing that nobody's actually going to get this answer correct. The answer is insects, particularly the eusocial insects. That means the ones who build hives and like bees and mounds like termites. So in fact, termites and bees are the best example of this. And this was the beginning of the war between architects and engineers. Termites represent the architects, bees represent the engineers, and the fight has been going on a couple of 100 million years, even before there were humans on the planet. They had this fight. So let me show you what I mean by that. This is a termite mound, and termites are everywhere in the world. I'm sure you have some species here in Chile. And if you ever see a termite mound, it sticks up out of the ground. But most of the termite nest itself is below ground. That's where the termites live and breed. And termites don't actually digest wood as we think they do. They bring wood to a bunch of fungus who eats the wood and digests the wood, and then the termites eat the fungus. That's what their food is. The fungus is very particular about the environmental conditions it likes, the temperature range, the humidity range. And so the termites have to keep the fungus at the right temperature for it to grow well. And that is the whole purpose of the mound. It is a designed ventilation, heating and cooling system where the little termites are opening and closing little holes on it all the time to get the right temperature. So they are the architects. They built a passive system for keeping the termite mound, keeping the fungus happy at the right temperatures. The bees were the engineers. They looked at that and said, that's way too much material. We can value engineer that down to something much more compact. And that's a beehive. The problem is that a beehive will be at the wrong temperature too often. And the way the bees fix that is they station bees at the mouth who flap their wings to ventilate the beehive. So that's the mechanical ventilation. That's the engineer's approach to it, is having an active system to do it. So that war has been going on for a long time. So let's get to where humans are on the planet. So we humans evolved a little over 2 million years ago. And as soon as we started moving into caves, we realized that we had to control fire by venting the combustion products. Fire is one of the most essential parts of human nature, and it's been around a couple of million years. And we had to learn to ventilate it in caves, because if not, people died. They figured that out. So if you look back into in digging things out of the ground, we see that 7,000 years ago in China, we can see what amount to houses that didn't have roofs, but they had, or they didn't have doors, but they had roofs with holes in them to allow for combustion. If we go to the Mediterranean and the Minoan Empire, which was the leading empire 4,000 years ago, they had a lot of designs as well. The Egyptians were very interested in ventilation. I'll give you a little story about it in a second. So here's an example of a cave that has no door, but that arrow points to a chimney. So that the people who first created this cave, probably not cavemen, probably not that old, but they knew the most important thing to do was to ventilate the fire, so they had a chimney. This is a schematic of the Palace of Knossos, which is on the island of Crete in the Mediterranean, which was the most advanced culture of its time. If you look at it, you see where the arrows go in terms of where air would flow naturally from ventilation. So the termites were very busy on this one. It's an interesting thing if you think about it. Given this sort of condensed picture, where do you think the king lived in his palace? And where do you think the storehouse in this palace was? Well, the king actually lived in the lower left there, in that one with the big blue arrow, because that was the one that got the best ventilation. So he didn't live on top. He lived in the bottom because that was the best ventilated. The top right was what they used for storehouses, because that had the worst ventilation. And also that space was called the labyrinth, if you know your Greek history, because people could get lost in the storehouses. So this civilization, who, by the way, were the architects of Atlantis, was very developed in a architect style. The Egyptians were also very concerned about ventilation. They learned an economic lesson. The pyramids were built by slaves, very highly trained slaves. Egyptian citizens wouldn't actually do work. They would be the ones counting things and doing it. And what they counted was they were losing more of their stone cutters, who were very valuable people. They were losing these stone cutters to health problems, which they figured out was because they were cutting the stones indoors. And the dust, they didn't know that, but the dust was causing lung problems. But they did know it was a problem, so they moved them outside to get better ventilation, so their stone cutters would live longer and therefore be more economically fruitful for them. So, but the first time we see ventilation being actually considered as ventilation was in the 17th century in England, where King Charles decided that you must have windows in your home. It would be a law that you had to have windows at least 10 feet, roughly 3 meters, high, and they had to be taller than they were wide. This was to allow for ventilation, stack-driven ventilation, and it wasn't retroactive, but it was a law that henceforth you had to do that. Miners knew that you had to ventilate. I think here in Chile you do have some mining, and these are wood blocks that were drawn in the 18th century from early miners. These are ventilation systems for mines that are wind powered, or if necessary, mechanically powered by people or animals, because if you didn't ventilate the mines, you'd kill the miners. Not a good idea either, much like the stone cutters of Egypt. So in English history, London tends to burn every few centuries, so there's a lot of great fires of London. And there was one in 1666. If you remember, in 1631 they changed the rules. So when London was rebuilt after that fire in 1666, there were a lot of windows, and everybody really loved it. It made the indoor conditions much better. But then the bureaucrats learned that everybody liked windows, so in the 18th century they started taxing windows because everybody wanted windows. So there's an interesting architecture. If you go to London, you'll find buildings that were built to look like they have windows, but don't, because they avoided the tax. Sticking with England for a while, also in the 18th century, the Parliament was declared foul, rancid, and pestiferous. It was never clear to me whether they referred to the building or its occupants in that rule, because nobody liked the members of Parliament. But in any case, when it burned down, they decided to rebuild it with a ventilation system. So this was the beginning of what amounted to ventilation standards, which we'll talk about for just a second. So in terms of building standards, the first one was 1700 BC, the Code of Hammurabi. It was a very simple performance code. If the building fell down, the builder was put to death. Very simple, easy to comply with, didn't need a lot of bureaucrats to figure it out. It wasn't ventilation specific, however, and that's what we really want to talk about here today. Since then, there were all these traditional practices like the Egyptians and the Minoans and every day where there were rules that people followed to what things should be. So that 1631 standard of King Charles was really the first one that was specific and quantitative to ventilation. So, and that led to the first science, really, of it. There was an engineer. Well, first of all, there was a doctor called Reed who wrote a treatise on ventilation. The English sort of owned ventilation in the 19th century. They did all of the work in the 19th century. And this Reed wrote sort of what's the Bible of ventilation at the time. And then they hired an engineer named Treadgold to design Parliament. And he came up with 4 CFM per person, 2 liters per second per person, as the standard that you should have to keep Parliament from smelling foul. I don't know whether it worked or not, but that was the standard. But from that time, the standard kept going up and up and up, and it was driven by infection control. So people like Florence Nightingale, Max von Pettenkofer, John Shaw Billings, these were all people who started recommending higher and higher ventilation rates to control infections. Florence Nightingale learned about that in the Crimean War, where people in tents were dying, but if they ventilated more, they died less. So that rate kept going up and up and up until ASHRAE was formed, as you heard earlier, at the end of the 19th century, 1894, which is the same, by the way, for its English counterpart, SIBSE. And at that time, the recommendation was 30 CFM per person, 15 liters per second per person, based on infection control. So that was the rate that was recommended. In the U.S., we had that rate, and by the early 1920s, we had a lot of the local codes using that rate in terms of CFM per person. They didn't actually know how to measure it, but that was the rule. So the engineers were winning. In the U.S. in 1927, the architects took over again and said, okay, enough of this CFM per person. We just have to have so many operable windows. So in the late 20s in the U.S., we switched over from being bees to termites again, and we said that all our buildings had to have so many holes in it to be safe. Then in the late 40s, in the American Standards Association, ASA, we switched back to CFM, and it was 10 CFM per person, 5 liters per second per person, and this was based on odor studies. By this time, sanitation and infection control were so good that we didn't worry so much about infection in ordinary buildings. Hospitals, yes, but not ordinary buildings. So the rate went down to 10 CFM per person, a third of what it was at the turn of the century. So the standard that that ASHRAE created in the early 70s was 60. The number was 62. Was an actual ventilation standard built first on that ASA standard that was from the late 40s, and it has gone through a progression starting in, the first version was in 73. The current printed version, which is the one I have here, is 2022. The 2025 one will come out soon because we reproduce it every 3 years. There's a lot of evolution that went on in the standard. I'm not going to go through all the changes because they're quite a bit, and I don't think we have time for that. But the most important thing is to talk about today is that it eventually came up with the concept of acceptable indoor air quality. And acceptable indoor air quality is two things. One is the air should not be harmful, and the second one is you shouldn't be dissatisfied. So the first one is about health, that you have to have a certain health criteria, and the second is one for basically odor, that it shouldn't smell bad. So that's the ASHRAE definition of acceptable indoor air quality. Now this definition is not quantitative. That's up to the standards to try to figure out how to do that. So where are those standards now? So in the late 90s, 62 split up into 62.1, which was the main standard for commercial and industrial, and then there was 62.2, which was residential. I was the first chair of 62.2, as I think you heard. And they've both been evolving since then. Other international standards, SEN, for example, has been doing it. Many countries have their own standards, but they're all progressing. So let me take a little side trip to talk about carbon dioxide, which is something that people misunderstand now, and I think let me try and clear it up. We can take questions about it later. So first of all, carbon dioxide itself wasn't a known thing till the late 18th century. Antoine Lavoisier, who's kind of the founder of modern science, found it in exhaled breath. So he was the first one to determine that we breathe it. But that's not very difficult to imagine when you think about we are just little unvented combustion equipment. We take in organic fuel, we take in oxygen, we generate energy out of it, and we exhale CO2, water, and of course we also emit a whole bunch of other things which are generally lumped into the word bioeffluent. But our metabolic activity is generated, we generate CO2. So that's quite a normal way to consider it. Now, how much CO2 is too much CO2? Well, there have been plenty of studies about that. Normal CO2 in outdoor air is roughly 400 ppm. Varies, of course, time of day, time of year, location, but roughly 400. The typical ASHRAE standard, the level you get in 62.1 typically will be roughly 1,000 ppm. That's roughly what you would get. And at that level, you don't have any smell from human bioeffluents, from human odors. Then in the range, until you get up to about 2,500 ppm, there are no actual known health or performance effects. There's some data on performance effects, but it's pretty weak. When you get above 2,500, you start to see actual impacts. 5,000 ppm is the occupational level. So if you are, a healthy worker working in a job, you can be exposed up to 5,000 ppm for your shift. But by 30,000 ppm, there's short-term acute health habits. So it can be a real problem if you get that high. So there are some studies that say you can see performance between 1,000 and 2,500. They're not very good studies because there are also studies that show the opposite. It's a very difficult thing to make these studies because to study people and their effects, you need a lot of people, and that's very expensive to do. So these studies are interesting, but they're not very definitive on what to do. So CO2, carbon dioxide, is not harmful to people at the normal levels in buildings. At any building ventilated to any modern standard, CO2 is not a direct harmful contaminant. But it can be used for controlling ventilation because we as people generate a relatively narrow range of CO2. If you measure CO2, you can calculate the ventilation rate per person. So that's using that is called demand controlled ventilation, and it allows you to control the ventilation rate if you want for the occupancy level to get the amount of airflow that you want. So that's a useful thing. It saves energy. It can optimize systems. But it's not really a contaminant of concern. As I said, no current standard of ventilation allows CO2 over 2,500 ppm. There's no direct physiological proof that anything below 2,500 ppm has a problem. The productivity studies are variable. Some show one thing, some show another. It's not clear that anything much happens below 2,500. There's a lot of bad data out there to talk about CO2 in that range, but not much good data. So why do we talk about CO2? Well, in part, it's because it's an easy thing to measure. But a lot of this is correlation. And as we know, correlation is not causality. Just because two things change doesn't mean one changed because of the other. And if you set out to prove that it does, and that's the way you set up your study, and you ignore the data that does it, that's called confirmation bias, and there's a lot of that happens. Now, when ASHRAE first looked at CO2 concentrations in its 62 standards, it found that the CO2 level of 1,000 ppm is what you got when you met the ASHRAE standards. And people thought that, oh, okay, I just have to keep CO2 at 1,000 ppm and everything will be fine. Well, that wasn't quite right, because if you started with 2,000 ppm and cleaned it by absorbing the CO2, the air still wasn't really right. There is no direct relationship between that. And ASHRAE understands that now. It spent years trying to fix that problem. There's a position document. You heard a little bit about position documents earlier today. There's a position document on indoor CO2, which is free on the website. You can just search for it and download it. And basically what that position document says is that the performance data, as I mentioned, is inconclusive. The link with airborne disease is indirect, meaning that it's not the CO2 which is related, but they might be correlated. And certainly measuring CO2 doesn't tell you how much particles or formaldehyde or other things you have in the air. It only tells you what CO2 is. So it's not a direct measure. So CO2 can be a tool. You can use CO2 for demand-controlled ventilation, but it's not actually a contaminant. What is it good for? Well, it's good for two things. One is because it's a direct link with human bioeffluents, odor, then we can set a limit based on odor, and it's around 1,600 ppm. That's the number I use. Could be a little higher or lower, depending on how you want to set it. But if you get 1,600 ppm, due to outdoor air, you now have diluted human bioeffluents enough so it's not going to smell inside. The second thing is it can be used to control ventilation using a demand-controlled system. If you know how many CFM or liters per second per person you want, you can figure out what that means in terms of CO2 and have a control system. So those are the two things it does work for. We're not protecting anybody from any kind of harm by controlling CO2 in any of the ranges that we do. We're not learning anything about controlling other contaminants. We're not learning anything about sanitizing or disinfecting in terms of infection control. And if you have too much more outside air than you need, you're just wasting energy. So I can answer more questions when we get to the question and answer center, but basically CO2 is not as important as people think it is. But let's talk about what might be important as people think it is. So you saw, Connie showed a map of lots of contaminants. Here's another picture of lots of contaminants. There are many contaminants in the indoor air, some from indoor sources, some from outdoor sources. In terms of indoor air quality, we want to make sure that we have low enough of all of these things so that we have a good indoor air quality, including odor. So there are two approaches to doing this. I call them the hazards approach and the harm approach. The hazardous approach is the traditional one. It's what's been used in 62.1 in the indoor air quality procedure. It's what you see when people say, the limit is some number. It basically says there is a hard limit, and you stay below that hard limit for each and every contaminant. So that's a hazardous approach. Everything which you think is hazardous, you set a limit, and you say it's okay if you meet all of those limits. Now, of course, we know that has to be wrong because it's not that different to be 1% above or 1% below the limit, but that's the way the hazardous approach works. The harm approach basically says that a certain exposure to a certain chemical or any kind of contaminant is going to cause you a certain amount of harm, and we should limit the total amount of harm. Doesn't matter where it comes from, we want to limit the total. That's the approach that I'm going to talk about for the rest of the session, and that's what 62.2 basically deals with. So let's talk a little bit about harm. I'm going to talk a little bit about harm. Ben Jones is going to talk a lot about harm in his talk, which happens later, so I'm going to be a bit quick, and hopefully he'll fill in the gaps, but I'm going to show you some of the important stuff. So how do we get to acceptable indoor air quality for 62.2? First of all, we have to look at a couple of things. One is we understand we're dealing with a chronic issue. We're not dealing with a 1 hour exposure. We're dealing with what's the average exposure over the year, what's the harm over the year. So it's a chronic effect, a long-term effect. And we need a metric to do this. And the metric is disability adjusted life years. And Ben will talk a lot more about why that's a good metric, but I'll just tell you that the medical profession has used it since the 1990s. The lawyers have used it, governments have used it. It's not a thing we invented for indoor air quality. It wasn't even, it wasn't used by indoor air quality till we did, but it was broadly used for all sorts of harm calculations. So how do we get to a harm approach for 62.2, for an indoor air quality procedure? So we have to look, first of all, most of the data is in the literature. We can't make new data. It's really hard. There has to be a lot of data out there. We need to know what's out there, what are the contaminants of concern, and how important is each contaminant? How much harm is each contaminant give us so that we know what the total harm is going to be? That's called the harm intensity. And then we're going to determine, by knowing what's typically out there on the harm intensity, which are the contaminants of concern, which are important, which are not. The most important thing is finding out what's not important so you don't have to deal with it. And we're gonna do that. So this is a chart of 45 contaminants that we looked at. Why 45? Well, it's because those were all the contaminants that we had the data to do this study for. There are thousands of contaminants in the indoor air. Most of them don't matter at all. These are 45. I do not expect you to read what's here. I'm showing you this to show you the variability of the concentrations that are out there. If you'll notice, it's on a logarithmic scale, so that there's 10,000 times more of some things than others in terms of micrograms per cubic meter. It's huge. I want to point out one of them in particular. Near the center, near the top, there's ethanol. That's the highest one that's there. So this is a survey all over the world of all the data we could find in people's houses. Apparently, people drink ethanol. Who knew that people would drink ethanol in their homes? But anyway, there's a lot of it in the indoor air. So you might think that's really important. But we may find out differently in a second. So we want to look at several different kinds of harm. Actual harm, what's really happening to you. Typical harm, which would be over the entire population. And what are the contaminants that generate that typical harm? For that, we need the harm intensities, as I mentioned earlier. These are the harm intensities, which tell you how much microgram per cubic meter of each thing matters. So it's intrinsic to the chemical. This is how harmful that contaminant is. Again, I'm not going to read them all. I'm going to point out one of them. If you look, there's one that almost touches the top near the left. That's the highest one. That's a chemical called chromium-6. Very harmful. If you ever saw the Aaron Brockovich movie about the cancer there, that is the chemical that caused that cancer, so very harmful. The other ones that are near the top, you can see that are green, which just indicates how we got the data, are the particles. So if we now put those together, the harm intensity and the concentrations, we now get a list of how harmful each of these contaminants is in the population of homes that we care about. And we only really care about the top ones. So remembering that this is a logarithmic scale, there's only a few that are up near the top that matter. If you look at our friend ethanol and also chromium-6, they're down in the noise. Even though there's a lot of ethanol, it doesn't actually harm you very much. And even though chromium-6 harms you very much, there's not a lot of it. So neither of those is important. This is one of the reasons why the concept of total volatile organic compounds, TVOCs, is utter nonsense. Because you can't add the concentrations together in any meaningful way, because as you saw from the harm intensities, some are much more harmful than others. TVOC itself is dominated by ethanol, and ethanol doesn't harm you very much. So if the number goes up or down, it doesn't really tell you anything useful. So if somebody's trying to sell you a TVOC monitor, don't buy it. Now I'm going to make the data simpler for you. Instead of all those charts, I've combined them into one chart that tells you what's really important and what's not. So first of all, if you look all the way over the right, the gray bar, you see that there's 39 contaminants that altogether don't even provide 1% of the harm. Basically, we can ignore those. So that's great. We don't have to talk about chromium-6 or ethanol or all those chemicals with long names that you couldn't pronounce. None of those are terribly important. The most important one is the one on the left. That's particles. Basically, what we found out that particles, PM10 and PM2.5, really are like two-thirds of the problem, over two-thirds of the problem. Most of the problem of indoor air quality is from particles. The next two are also important, nitrogen dioxide, which is from combustion products, and formaldehyde, which is from building materials. These two are also important. They're in the order of 6% each, so those are significant. The two in red are only 1 and 2% from a population point of view, so that's ozone and radon. But those are not distributed evenly. So ozone is a problem in urban air basins that get smog. Perhaps you know of one. I don't know. I grew up in Los Angeles. That's one. And radon is a function of the soil that you grow in. There's some places that have a lot of radium in the soil, and you get a lot of radon there. So when it's important, those are important, but those are very local, and you know when it's important. You have an urban air basin that controls the air. They may make special requirements. You live in radon country, you may have to put in radon technology in your basement. So there's really only 3 contaminants that matter very much, and that's important. So now the approach that we're doing in 62.2, it has 2 main requirements instead of a ventilation rate. The first requirement is odor control. And you can do that in 2 ways. One is you can control the CO2 to 1600 ppm. So again, that's a good use for CO2. Or you can have 7.5 CFM per person, 3.5 liters a second per person of a base ventilation. So that's as low as you can go. That's the base level that you have to control odors, because there's no other good way to control odors. Plus, you have to have the second requirement, which is a harm budget that tells you you can only have a certain amount of stuff that harms you in the air. If you can't remove it from the source or filter it out, then you have to dilute it with more ventilation. So this is the equation we use for the harm budget. So it's just taking the 3 concentrations, each of which has a weighting factor, and making sure it's below some threshold. And that's the way it's presented in the standard. One of the issues, of course, is that you can't real-time measure all of these very easily. In theory, you're allowed to do that. You can do that. But it's not easy or cheap to do that. So we have alternative methods for doing it. For each contaminant, there are alternative methods to measuring it directly. You get defaults depending on what the configuration is. For example, if you don't have any combustion equipment, you get a very low default for NO2. For particles, it depends on whether you have filters in your system or not and how often you run them. You can get lower values. You cannot just use the default values of all these and pass. So you have to do something, either measure or take some of these reduction measurements to do it. One of the points is this is made equivalent to what the ventilation rate procedure is. So the rates in 62.2, which if you can ignore all of this, you can use those. This should provide the same protection as those rates. So the summary of that proposal is basically that you control for odor with either minimum ventilation or a CO2 control. And you do a harm-based analysis to figure out if your air is clean enough or if you have to add filtration or some other effect. And you only have to look at 3 contaminants: particles, formaldehyde, and nitrogen dioxide. So that makes it doable. Now, nobody's done it yet because it hasn't quite finished going through the ASHRAE review process, but we're hoping it will soon, and then people will start to do this. So I'm not talking much today about infection control, which is standard 241, but ASHRAE standard 62 has never been based on infection control. As I mentioned earlier, infection control was split from the standards a century ago and left to the healthcare people to do it. But since COVID, ASHRAE has gotten back into the infection control business. That is what standard 241 is about. It's about how you protect from epidemics. And if you want me to give a lecture on that, you'll have to ask me back because I don't have any time for that. So in summary, ventilation and indoor air quality was first about combustion because that's what was the big polluter then, was fire. Then we went to odor control, then we went to infection control, then we went to odor control. Now we're talking about both odors and hazards in 62.2, and we're hoping that the harm paradigm itself will soon become more common. So with that, thank you.
Muchas gracias, Max. Qué orgullo tenerlo acá, ¿no? Un gran invitado. Bien, ahora vamos a pasar a tomarnos un cafecito, galletitas. Nos encontramos a las 10:20. Uno de los requerimientos de ASHRAE es hacer una encuesta a los participantes que están aquí presentes. Así que, por favor, los invito a llenar una breve encuesta al momento de salir, que después vamos a recoger, ¿ok? Y después seguimos. Bien, muchas gracias. Espero que hayan disfrutado del coffee. Nuestra siguiente invitada, Valérie Leprince, nos viene a visitar desde Francia. Cuando recién le escribí para invitarla, se demoró menos de 24 horas en responderme ¡sí! Y le prometí de que la iba a dejar en algún lugar donde pudiera correr, porque ella es corredora y gran viajera. Así es que logré, yo creo que satisfacer, espero, sus dos pasiones, aparte de las consultorías. Ella viene de una institución francesa que se dedica a la implementación y a trabajar con la industria, y en especial con temas de hermeticidad y calidad del aire, y ventilación, obviamente. Y nos viene a contar un poco cómo lo hacen en Francia. Yo quiero saber cómo ellos lo están haciendo, cómo lograron organizar las instituciones, el cumplimiento de las normativas, el tema de la capacitación a las personas que van a hacer inspecciones y cómo después ellos trabajan los datos que se van recogiendo para poder aprender sobre la forma en que nosotros edificamos y operamos nuestros edificios. Así es que les pido un gran aplauso a Valerie y que disfruten su presentación.
Hola. No voy a utilizarlo, voy a caer, si no. Pues soy Valérie Le Prince. Constanza le ha dicho, voy a contar muchas cosas, pero lo siento, voy a hacerlo en inglés porque, pues, no sé si no lo siento o que no se preocupa, voy a hacerlo en inglés. Mejor, probablemente. Well, so, yeah, I'll speak about the strategy for ventilation and building airtightness in buildings in Europe, not just in France, but, well, of course, I know better the French subject than the rest of Europe, but still, I'll talk also about a little bit about our neighbor here. First of all, very important things, I would say, we should not mix ventilation and airing. Those are two very different things. You've got multiple ways. No, this is not pointing. Yes, it is? No. We've got multiple ways to deal with indoor air quality. The first thing to do is clearly to control pollutants, okay, to limit the quantity of pollutants you emit inside your building. That's the first thing to do. But you cannot avoid everything. You still need to take some shower sometimes, or maybe to cook also. And this, you need to remove those pollutants by changing the air in the building. And you've got there are three different ways that the air may change in the building. The first one is ventilation. This is a means that you control, where you know where you go. You know the amount of air you bring in, and you know the amount of air you remove from the building. The second way is airing, which is sometimes mixed with ventilation. The problem with airing is that you have absolutely no control of the amount of air that you bring in and that will get out. And you have absolutely no control at when it will occur. Okay, some people say, well, it smells bad. I open the windows for 5 minutes and that's just fine. Yes, of course, if your nose was a very good sensor, that would be just fine. But your nose is usually not able to detect the pollution event in your building. And sometimes it smells very good, but that's very dangerous for your health. Doesn't mean the feeling you've got is not necessarily correlated with the impact on health. So airing is a good way. I mean, if you just painted all the bedrooms, good. Open all the windows, that's now you should do it. But it's not the way to ventilate the building on everyday life purpose. Infiltration, exfiltration, what is it? It's the air that is coming through not intentional leaks inside the building. All these little leaks beside the windows, on the plugs, etc. You don't want those leaks. You don't want those infiltration. This is the problem of air tightness. Okay? So infiltration is the air going through air tightness defect. In ventilation, you have three ways, basically, of doing it. Either with the mechanical ventilation, so Max told about the bees, okay? So that's, we don't use it that much, but usually we put a fan nowadays. The other way is natural ventilation. Natural ventilation is not airing. Natural ventilation is a way to renew the air, but has been designed and is purpose provided. So it can be used through windows. For example, we have more and more in Europe windows that automatically open when the indoor air quality with sensor is not good. Then the windows will open. It will renew the air, and when it will be done, then it will close, but according to the sensor inside the building. And the best way to do it maybe is through hybrid ventilation, where you mix natural and mechanical. When natural is not enough, then the fan come here to help it. So that was the first thing that was very important for me to explain, that when I'm talking about ventilation, I'm not talking about airing. So, this is explaining this a little bit more, but ventilation is the process in which clean air, so usually outdoor air, this is why I put the clean into bracket, is intentionally introduced into a space from which stale air is extracted by appropriate purpose-provided means and design means. It's different from the leak, which are unintentional, and it's different from the airing, which the air is introduced intentionally, but not through purpose-provided means. One very important thing to remember is the motto of the AIVC, I will talk a lot about the AIVC, is that for a ventilation system to work well, you need the building to be airtight. And when the building is airtight, you need to have a ventilation system that does works well. Why is that? If you've got, for example, an extract-only system, you know, a fan in the bathroom or in the kitchen that is extracting the air, okay? If you've got a huge leak right beside it, the air will take the shortcut, okay? Enter through this leak and get out through the fan, and you won't have any ventilation in your bedrooms. This won't work. I see Gilles, who has done a study on this subject and can share it here in Chile. So really, if you want to make efficient building in terms of energy, you need them to be tight. But if your building is tight, you need to have a ventilation system that will remove stale air and provide good indoor air quality. So now, what is building air tightness? So I won't go through much detail, but basically, this is the general terms to express the resistance of inward and outward air leakage through unintentional leakage paths. You should not mix, when you're speaking, air tightness, permeability, this is basically the same thing, with infiltration. Infiltrations go through leakages, but the value of air tightness is the amount, basically, of leak that you've got in the building. And the amount of infiltration you will have will depend on this amount of leak, of course, but will also depend on the wind pressure, the temperature difference, and a lot of things. So the amount of leak does not guarantee that you will have a certain air renewal in your building. It will depend on temperature, wind, etc. We've got lots of studies, and we've done a full literature review on the AIVC to explain why it was important to build airtight building. Those review, I think the first data we got are from the 80s. Probably Max was co-author in that at that time. I was not. Barely born, so I was not, but we've got a lot of studies that show that under her climate, which is also your climate, building airtight is efficient in terms of energy, and basically you can usually save, let's say, 15% between what you will do if you don't care and what you will do if you care. Building airtight does not cost more most of the time. It's just a matter of caring. It's just a matter of designing. It's just a matter of taking it into account from the very beginning. You see this line here. When you first design the building, you need to check every space, every place where there is potentially a leak, and find for the solution for this specific leak. Usually it's just adhesive, glue, membrane, or maybe mastics, but it doesn't cost much. But you need to take it into account from the very beginning. And if you take it into account, usually the energy saving is around 15%. We already discussed indoor air quality. If your building is not tight, your ventilation won't work right, and you will got problem with the indoor air quality. There is also risk of building damages. There is a risk, really, of moisture that will build up in the structure and insulation material if you've got humid air transiting through leakages. So that's another problem. And you may have mold development also around leaks. And you don't want to have mold development around leaks. You don't want to have mold development in your house for multiple reasons. That's not very beautiful to have a lot of mold in the roof, but also this is not healthy at all. Okay? And another reason is safety also. This is in some region of France, and now more and more, we use the airtightness of the building as a shelter in case of explosion, for example, in industrial plants. So for houses that are built close to dangerous industry, they need to be tight, and they need to have a tight space inside the house. In case of explosion, the people can stay safe in the houses. Actually, this argument for building airtight, the safety argument, is now really used in Greece. I was discussing it with a Greece colleague. They have had massive forest fire in Greece, and they are actually using this argument of airtightness to say, okay, let's build tight so that if there is a fire outdoor, we can stay safe inside. Safe, well, not safer. Yeah, safer is better than safe. So, to build efficient building with good indoor air quality, one needs the right amount of fresh air coming at the right place and at the right time. Okay? So, well-ventilated, airtight building. Now, to make sure a building is airtight, of course you have to design it from the beginning. But the thing that you have to do is to check it when the building is finished. Well, under construction, even better, and then when the building is finished. It's easy to say, yes, I have done everything. My building will be tight, I'm sure. Let's not check. This usually doesn't work. I mean, maybe in some countries it works. It doesn't work in France at all. In Switzerland it works, but I mean, not every country are Swiss. So the usual way to do it is to use a blower door test. So this is this door you see here. Basically, you switch off the ventilation system because, of course, you've got a ventilation system if you have built a tight building. You switch off the ventilation system. You seal all the air inlets that are purpose provided for the ventilation. You install the blower door on one of the door or windows, and then you plug the computer, and then you start to either depressurize or pressurize the building. Okay? And then what you measure is actually the pressure difference between indoor and outdoor and the flow rate that you get with this pressure difference. This is how you check the airtightness of the building. Okay? And then you calculate the airtightness indicator, whatever it is, we will come to that. A good thing, a good practice when you are doing airtightness tests is also to locate the leakages, to find out where are the leakages so that you can solve it in this specific building, but also that you can solve it in the future buildings that you will do. There are multiple ways to do leakage location. You can use smoke. Okay, so you put the building in negative pressure and you go around the building with some smoke and check where it's going on. There are acoustical methods also, but one method that people love usually is infrared thermography, because this is very good for your client. You bring this picture and it shows immediately where the leaks are. The thing is that you should not mix leakages and thermal bridge. So the good practice to do so is actually to make two pictures and subtract it. So first, you take a first picture of the place without doing any depressurization. Then you put the building under with negative pressure. You need to have at least 4 degrees difference between indoor and outdoor for this to work. So indoor needs to be 3-4 degrees hotter than the outdoor. Then you take another picture and you actually subtract the two pictures, and this is where the leaks are. So if you were just using one picture, you may have said, oh, I've got a lot of leaks here. In fact, when you do the subtraction of the two, you see that this is no leaks. This was just thermal bridge. Okay? So this is why it's important to make the subtraction between the two. If you want some more information, as I said, I will talk a lot about the AIVC. All the AIVC resources are freely available on the AIVC airbase, so you can download everything. It's all in English, but now, I mean, ChatGPT can translate it to you in any languages much faster. So, I mean, that's easy. One thing is, to test building airtightness, there is not one standard that the full world would apply, because it would be too easy. So there is one standard that the full world is supposed to apply. This is an ISO standard, ISO 9972. So of course French people apply it because we always do things right. But the American has said, no, let's do an ASTM because we know better. The Canadian have done their standard, which is actually pretty good, so I won't say anything about this one. The Japanese have done their standard also, because it was much, much before. They were the first one to test airtightness, so they've got a very old standard, very, very fancy one. But they no longer test airtightness, but they still have their standards. The thing is, in fact, the way you test airtightness will depend on your national requirements. So this is why we need to customize a little bit the international standards. And you'll see that, if you want some more information, as I said, in the AIVC, we have done a review in those 13 countries. about how airtightness was taken into account. So there are European countries, but not only. You see, we've got Korea, Japan, New Zealand, USA. China also has made its own paper. So if you want to know exactly what is going on in terms of airtightness in China, you just download this paper. It's explained. All of them get the same template, and so you've got the description of what is in the regulation, how they perform the test, etc., etc. I would love to have one from Chile, so I look at Gilles and Constanza. Maybe they will make an airtightness test for Chile at some point. And then we have done a review, which is in the TN 73, and and I'm still waiting for the British one actually. So I'm also looking at Ben on this one, and then. What we have done first is to try to compare which kind of indicator for airtightness country use. The old indicator that has been used for years is N50. So this is the flow rate if there is 50 Pascal of difference between indoor and outdoor, divided by the volume of the building. This is what the N50 is, basically. It has been used for years. But not because it has been used for years means that it is the best one. And actually, in my view, this is not. It's more relevant to divide not by the volume of the room, but to divide by the envelope area. Why? Because this is where leakage are. Leakage are not in the volume. Leakage are on the envelope. So to assess the quality of the construction, it's better to divide the flow rate by the envelope area rather than the volume. So this is why more and more regulation now are turning from N50 to what we call QE50, which is the same thing but divided by the area. While in France we've got something different. We divide by the envelope area, excluding low floor, because we assume that most of leakage are not coming from the floor. That's a bit stupid, so I won't go too much into details into it. And also not to make things like the other. Instead of using the flow rate at 50 Pascal, we will use it at 4 Pascal, because this is more like what the pressure the building will see when it's under operation. But, well, let's move away from the French indicator. I'm not very proud of this one, so I'll just say that QE50 is probably the most relevant one. Now, what about mandatory requirement in countries in terms of airtightness? One interesting thing is we've got multiple countries that say the airtightness of the building should be this. You should build all your new building with this value, but actually do not make a mandatory validation. Do not require that the building, the airtightness is actually checked at the end of construction. So those are the light countries. Those are light green. For example, Spain, Germany, Netherlands. They say, okay, you've got to have this value of airtightness, but you don't need to check it. Guess what? It usually doesn't work. And we've got a much more interesting country, which is Belgium. You see it in red, because they don't have mandatory requirement on airtightness. You say, would it be interesting? Because they are testing almost 100% of the building, even if they don't have mandatory requirement. How have they made that? What they did is to say, no, you don't need to test airtightness. You don't need to have a value. Do whatever you want. But just if you don't do it, you need to take a default value that is so high that it will jeopardize the energy performance of the building. It's so high that whatever you do, you'll do better than that. So for the people, it's much easier to say, okay, let's test it. Use the real value in the energy performance calculation. Whatever it is, it will be better than the default value that is that high. It will be much less costly than try to... I mean, they had to add 30 centimeters of insulation if they want to compensate for this high value. So much easier to test the airtightness. So Belgium example, in my view, is a very good example, a very good way of actually requiring airtightness without saying so in a very efficient way. In France, in the UK, in Ireland, we've got mandatory requirement on airtightness, and we need to justify it. So not necessarily by a test of all building, we can test only samples, but at least it needs to be justified. Here is basically the amount of tests that are performed in country in residential and non-residential building. You'll see what I was saying. Belgium is almost at 100%. France, we are at 30% for residential building because of those sampling rules and the quality approach also. And, well, most of the country are below 30%, I would say. Those are, well, data from expert sites, I would say. So it's not really published somewhere. It's not so easy to know which percentage of buildings are tested, but professionals usually have a gross idea. So, national guideline to perform airtightness tests. As I said, you need to customize basically the airtightness test, because every building, every country has its own specificities on how we build, what you will find in the building, what is important and not important in the energy performance calculation, etc. So usually, you would agree to say, okay, the opening for the whole building mechanical ventilation system, of course it needs to be sealed. No debate on that. If you ask all the countries, they will say, yes, you need to seal that. That's easy. Well, ventilation opening for natural ventilation, well, not everybody gets the same answer, but in general the idea is that it should be closed or sealed. But now, if we come at very specific things, like, okay, what should we do with the air exhaust of a clothes dryer, for example? How do you prepare the building? What should you do with that? Should you seal it? 2 countries says yes, we should seal it. Should you close it? 3 countries say yes, we should close it. 2 countries says we should leave it as it. And 1 country say you should make sure that it remains open. So actually, there is not a general, even if there is an ISO standard, all those countries are using the ISO 9972 standard. So they're using the same standard at the beginning, but they don't have the same interpretation because they don't have the same problematic, the same energy performance, the same acoustic requirements, the same blah, 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 the same regulation for the rest of the subject. So you need, if you make the test mandatory, to have a text for the Chilean context that says, here is how the test should be done precisely in Chile, so that you can compare the result from one test to another. Otherwise, you will have testers saying, hey, don't worry, I will make you pass the test, I will just seal everything around, and that will be fine, okay? You need to have precise rules, so that you've got the requirements that mean something. So here in green, this is all the countries that have actually developed specific rules for their country to explain how to perform the building airtightness test. And here are the country in green that have developed a qualification for airtightness testers. Okay, I did zoom on Europe, not because I think that Europe is more important, but we are so much little countries that we cannot see anything if I was keeping it at the right size. So, and also I'm missing a lot. I don't have any information of what is going on in Africa, so I did that. So all those countries in green have set up a qualification for airtightness tester to make sure that the requirement was actually well implemented. If you want that the people accept your requirement, it needs to look like serious, I would say. If anybody can come and perform an airtightness test the way he wants, it will discredit the regulation. It will mean that, okay, you can get the value you want, just take the one that is doing the test the right way so that you reach the value. No, you need people that are trained, that know how to perform the test. When I say train, I'm talking about a 2 or 3 days training. It's not very big deal. It's not a 3 years college graduation, but so 3 days training to know how to perform the test and to perform it right. So in France, we've got this qualification, and only people that are qualified can perform the test in the context of the energy performance regulation. Same is Belgium, no requirement on airtightness, but a qualification for tester that perform test in the context of the energy performance calculation. Also, what we get if you want to have a requirement on airtightness is to provide guidelines for craftsmen to actually build airtight. As I said, it's not a big deal to build airtight, but you need to know how, and you need to plan it from the very beginning. So I'm sorry, this is in French now. After English, we learned a lot of language today, but those are from 2010, the very beginning of the regulation in France. We provided them construction details and saying, okay, here is what should be done at the masonry level. Here is what should be done when you do the windows, the electricity, the plumbery, and we provide technical details explaining actually how to make sure that those links are really airtight. Okay, and this is suitable for the French context, for example. It may not be suitable for the Chilean context because you don't build the building the same way. I have seen since I'm here that your windows, for example, usually go to the top, almost to the ceiling in multiple buildings. This is not in France. We always top the windows at least 30 centimeters before the ceiling. That's just construction habits. I don't say one is right and one is wrong, but you need to have adequate construction details that do correspond to your construction habits, which are not French, which are not American, not either Belgian, it's just Chilean habits. And one very good thing, when you do perform airtightness tests, and when you have qualified tester to do so, is to set up a national database for airtightness. I love our national database. So there is one in the UK with the ATMA database. France get one, Belgium get one. Czech Republic also has one. Greece is starting to have one, but they don't perform that much tests. But still, that's a very great tool to improve practice. So, for example, in the French database, we've got around, let's say, 60,000 new data per year that are added in the database. All qualified testers need to feed in the database every year. Mostly for single houses, because we don't have mandatory tests for non-residential building yet. And then we can see really how the new regulation in 2012 has really induced an improvement in building airtightness. So yeah, I know this is a lot of data. I don't really like this graph, but on the left of the line, this was before the regulation, and after it's, so we see that in average we have basically divided by 2 the value of permeability of the building, so improve the permeability of the building thanks to the regulation. There is still some discrepancy, and since the regulation, in fact, it's quite stable, because they don't try to do better than that, they just try to reach the required level, but as soon as they understood how to build airtight, now it's just implemented as it is, and it remains quite... the test is not really necessary now because they actually know how to build airtight. Another thing that we have in our database is that the tester, when he came in, have to do a leakage detection, search where has the leakage, and put it in the database where he has found the leakage in the building. So we actually know that 29% of detected leakage were around windows, that 19% of detected leakage were around penetration in the building, and 23% around electricity plugs, okay? Or lighting plugs, I would say. But what we saw, we've got all this, way of defining in categories all the leakages. But what is interesting also, so again, you won't see anything in my graph, I'll just explain it to you, is that we can also make a correlation between the leakage detected in the building and the actual level of airtightness. And what we see is that when this leakage before, so that's the first one, is detected, the airtightness of those buildings are actually higher than the others, where this leakage is not detected. So this leakage seems to be the one that is the most impacting the global airtightness of the building. So this is the one on which you should work. And this leakage specifically is the junction between the wall and the ceiling. If it's not tight here, usually your houses will got some problem to pass the test. Well, I got some other thing on it. So this is it for airtightness. And now, if you've got an airtight building, because with that you will have an airtight building, you need to have a ventilation system that perform well. This is very important, and this is not obvious, even if you've got a requirement on ventilation, even if you've got the best regulation ever because you have copy 62.2 that has been done by Max, so of course that's the best, doesn't mean that you will have a good ventilation system in your actual building in Chile. I'm not saying that Chileans are not able to build a ventilation system, not at all. I'm saying that nobody is able to build ventilation system if the work is not checked after construction. In France, well, maybe we are very bad at it, but still, In France, we have had a regulation since 1983. I do remember, that's my birth date. So more than 40 years old regulation. The same regulation, it has not changed, and it's a very simple one, even simpler than 62.2. Well, before the new regulation 2020, so let's say in 2019, we check how much dwelling were actually complying with the regulation. A 40 years old regulation, nothing new here. We found out that almost half of them were not meeting the prescribed flow rate in the regulation, okay? And 2/3 of them were not meeting the regulation because, for example, they don't have the right air inlet in the bedroom, you couldn't access to the fan as you are supposed to be to do the maintenance, etc., etc. So this regulation has been to force for 40 years, and after 40 years, people were still not able to implement it correctly. Why? Because there were absolutely no control. So they were doing things. Nobody can tell that. Can you tell me what is your ventilation system performing right in your building? Of course not. The best thing you can do is take some toilet paper and check that it actually sucks the air from the building. But that won't give you the flow rate. That won't ensure you that you've got the proper ventilation rate, right? So if you don't have a proper commissioning, you have, let's say 1 chance out of 2 that you won't have the proper flow rate in the end if you're building. This implies health risk, occupant discomfort, and energy efficiency, usually. So you've got, less than half of the world that meets the ventilation flow rate with incorrect installation, usually. You've got the wrong terminal positioning, crushed ducts, disconnected ports. It's a mess. I will show you some pictures so that you can really see what I'm talking about. And so what I want you to keep in mind is that if you build an airtight building, you need a ventilation system, and this ventilation system, at the same time as you test the airtightness, there is no reason to do it in another place, you just commission it and check that it's working as foreseen. So it's now mandatory in France since 2020 to do this checking. I just give you some example of things that we can see. The furniture, it was not convenient, so let's just cut the air terminal so that it fits. Clean it, well, it's supposed to be done every year. Why should we do that, right? It's nice when it's dirty too. This woman thought that the ventilation system was noisy, so she just put some kind of handkerchief or I don't know what in the terminal. Here, it was not convenient because they needed to put the furniture right at the place where the duct was coming. Then why matter? I mean, you just cut it up over and put the terminal over it. Oh, it comes not to provide the required flow rate. What a surprise! Here is a funny one also. You've got this air inlet, this kind of air inlet here. So here it's upside down. That's not too difficult to solve. And here they put the air inlet and realized that there is no hole behind it, which make, of course, the air inlet in much less air. So, they try to solve it by drilling some hole, but not enough. So, and I can go on for 2 hours with those pictures. We've got plenty of them. I love this one also. Who could assume that the flow rate, the air will go through this kind of ductwork, right? I mean, and here, I love, this one is one of my favorite because we don't see the problem at first, okay? So this is the ventilation system. It goes here, it's supposed to blow the air out, okay? But they happen to forgot to make a hole here. So it blows in there. Yeah. And I love also the creativity. I mean, they are real artists, some of them, with the ductwork. They can, by the way, do not use this kind of ductwork. Those are rubbish, really. It's a mess. So flexible ductworks, very bad. And here, the connection was almost airtight. It will ventilate the birds, it's also important to give them some air. And here I like this one also. It's mandatory that you can access to the ventilation system, so you need to have a trap to access it. But if you put the duct right in the middle of this trap, it's become much more tricky to access it. You need to be, maybe Connie, you can go through this one. Yeah. So, if needed, you can ask. But, okay. So what is a good inspection of ventilation system? First, you check, before going on site, you check what you are supposed to find on site and check that what is supposed to be installed actually meets the regulation and there is a proper documentation that goes with it. Then you perform the inspection first thing is just a visual inspection. Just check that everything is where it's supposed to be. It's already very important, and you will find already a lot of mistakes here. Then you perform functional measurement. Usually it's flow rate. It's maybe also only pressure difference if you've got a humidity-based demand control ventilation. And, well, you can also perform additional measurements, such as the power of the fan or things like that. And in the end, very important, you provide an inspection report. Saying that you have inspected the building is good. Proving it and showing the results is better. Why? Because if someone else come on site then and say, the ventilation system is not working, yes, it has been checked, show me. And now you can say to your client, yes, it has been working, it has been checked by a third part. So, another thing, so now it's mandatory in France, as I was saying. And also we've got this National Observatory for Ventilation. And so now all those reports that I was talking about are filled online, and you can see what are the most defects that we find in the building. And again, the idea is to help builders to focus their work on what really matters and where the problems are in the end. As you will see here, we also get statistics on the kind of ventilation system we've got in France. So 96% at least humidity-based demand control extract-only ventilation system. So basically, on every windows of bedrooms and living room, etc., we've got an air inlet. And in every bathroom, toilets, kitchen, we've got an extract system that will vary with humidity level. Well, not in toilets, of course, that would be stupid. In toilets, it varies if there is someone or not someone in the toilet. But in bathroom and kitchen, it varies with the humidity level. And most important of everything is that this system is running 100% of time. 24 hours, 7 days a week. In residential building, you need to have this constant flow rate for the system to perform well. Otherwise, it can be decreased to a minimum, but it needs to run constantly to remove the humidity that is constantly produced in the building. Okay? You need to brace 100% of time. The building needs to brace also almost 100% of time. So if you want some more information about ventilation requirements in countries and inspection, etc. You also got this series of VIPs that are published. We've got 4 of them now, if I'm not mistaken. Ireland, France, Spain, and Italy that's just been published. So if you want to have a look, also you can find it on the AIVC airbase. And the kind of control that are performed usually is for energy performance, indoor air quality, acoustic, and thermal comfort. So now, just one last slide, and then I will leave Ben talk about health and ventilation. But although what I have talked about right now was mostly about prescriptive requirements, we have had very prescriptive regulation for the last half century, I would say. The idea was to say, okay, you need to provide this level of flow rate and you need to reach this level of air tightness. This is very prescriptive, and I think this is a necessary first step. But now we are moving toward more performance. So now the requirements, the European directive, what it says is that the requirements need to be basically, you need to write down performance-based requirements. So basically you say, doesn't matter how you build your building, but it needs to reach this level of energy performance, this energy use basically, and it needs to reach this level of indoor air quality. So we need to develop indicators to say what is good and what is a bad indoor air quality. And that's not that easy to say so. Well, health indicator, Ben will talk about it, but that's not that easy to agree on what is good air quality and what is bad air quality. Because good and bad are not the same according to the purpose of the building, to how it's used, to by who it's used. I mean, you won't have the same requirement in a storage room than you would have in a classroom, right? And still, sometimes it can be very good in the storage room, but this won't be said as very good for a classroom, okay? So this new Energy Performance Building Directive has been published in 2024 in Europe, and members countries get 2 years to change their to adjust their regulation and to move to this performance-based approach that include indoor environment quality. So maybe this afternoon we'll have some time to discuss about how we implement it in France, but for now I think I have already passed my time by an half an hour probably. So I will, not that much? Okay. Wasn't not that bad. And so muchas gracias por su atención y hasta luego.
Muchas gracias, Valerie. Les dije que iba a ser yo la más aburrida de todos. Bien, para terminar tenemos ahora la presencia de Benjamin Jones. A él es el primero que conocí de los tres. Me presentó al resto también. Ha trabajado en temas de ventilación y calidad del aire en viviendas de Chile gracias a mi proyecto de investigación de doctorado y también un proyecto que realizamos en pandemia. Pudimos observar y evaluar recintos de trabajo, así que sabe del contexto chileno y nos viene a hablar ahora sobre las consecuencias de una mala calidad del aire en la salud de los ocupantes y qué podemos hacer nosotros ahora para regular estas condiciones. Así es que bienvenido, Ben, y muchas gracias por venir.
Well, good afternoon, everybody, and thank you very much for the invitation to be here. It is an absolute pleasure. I'm going to try and link a few things together because we've talked about standards, we've talked about why it's important to build tight, and now I'm going to talk about quantify the reasons why it's important to ventilate right. I think that one thing maybe we haven't made clear this morning is that both Valerie and Max and myself are all part of the Air Infiltration and Ventilation Centre, which you can find online at aivc.org. Everything on there is free. You don't have to sign up, you don't have to give your name, you can download anything from the 20,000 odd documents that are available documenting the evolution of ventilation theory over the last 30, 40 years. So, the work I'm going to present was done largely by a South American friend, a Venezuelan, Gio Morantes, who won a scholarship at Nottingham, only to find that his life savings were wiped out during the crash, the economic crash in Venezuela, which made everything he owned worthless. And to get him on a plane to come to the UK to do his work that I'm about to present and that Max has already introduced you to, I had to get the Chartered Institution of Building Services Engineers to sponsor this work. The curious thing is that the CIBSE, as it's known in the UK, has now funded work that's gone into ASHRAE. Air quality. I think if I had a conversation with most people, we could talk about indoor air and agree on what it meant. But we would argue strongly about what quality might mean. I've heard lots of calls for good air quality, for excellent air quality, for outstanding air quality. I don't know what any of those mean, and I don't think that they know either. And that's because quality is a measure of excellence, but it's also a relative metric. It's relative to something. So should good indoor air quality be relative to perfection or to the worst possible thing or something else? Go back to the definition that Max introduced before, which talks about harm here. And what it makes very clear is that ASHRAE's definition of acceptability, because ASHRAE is often criticized for having only acceptable indoor air quality and not good or excellent or outstanding, is that it is not a categorical variable. It is a binary variable. The air quality is either acceptable or it is not acceptable. Now, the criteria that make up the acceptability change over time as new evidence emerges. And I think we are just moving to a brand new way of thinking about things. The word paradigm is often overused in scientific contexts, but maybe really this is a new paradigm. There are, as Constanza pointed out, a whole range of contaminants that we are exposed to on a daily basis. They are emitted, they are dispersed, some of them may be reabsorbed, deposited, but we are exposed to them nevertheless, and we will inhale them. So depending on how much we inhale, we will quantify the dose of the contaminant that we are interested in. And then depending on how big that dose is, may affect the response. Now that response will occur over 2 time frames. Near immediately, which over the course of a day, so less than 24 hours, we would call an acute response. And that would make up things like a building-related illness or a sick building syndrome, depending on whether we know the cause of our symptoms. Those are the conventional terms that have been used in the past. If it occurs over decades, then it is a chronic symptom. And for the purposes of this talk, I'm only going to focus on chronicity. So as we're exposed to these contaminants over time, whatever they may be, we will start to experience some kind of ill health, and depending on the contaminant and the dose, we may lose our lives earlier or end our lives earlier. We started to think about this in the AIVC with a session in Brussels back in 2017. And our thinking at the time is documented in this ventilation information paper, but I would say we've moved on since then quite a lot. Now, most of the time, we tend to use exposure limit values, threshold limit values, which are a way in industry to set maximum levels, and traditionally things like machine vibration, but they also apply to airborne contaminants too. But one thing that isn't very clear when we use these numbers is what happens if you exceed the threshold by, say, 10%, or if you're under it by 10%. What happens? Is it good? Does it have a significant effect on us at all, or can we get away with it? I want to use here an example of exposure limit values set for PM2.5 by a number of air infiltration and ventilation centre countries listed in a well-known indoor air quality metrics database. So for PM2.5, you have Norway, the USA, Spain, and China all setting radically different exposure limit values for PM2.5. So even on the same contaminant, many regulation organizations cannot agree on what an appropriate number is. The World Health Organization sets exposure limit values for these 3 contaminants: particulate matter with a diameter of 2.5 microns or less, nitrogen dioxide, and ozone. And the values from left to right are 5, 10, and 60 micrograms per cubic meter. Remember these. I'll be coming back to these in a bit, and we can say what we think of them maybe later on. Now, Max introduced the concept of the DALI. There are a number of health metrics, econometrics, that have been created over the years. Actually, in the UK, we don't use the DALI. We use the quality, which is mitigated harm or quality of life gained by some intervention. Normally it's a drug. We use this in our National Health Service, which is a socialized healthcare system, which is why it becomes so important. We set a maximum value for a treatment, and it's based around quality adjusted life years gained by that treatment. Most other countries don't use QALYs. I think only the UK, Thailand, the Netherlands and a few others use them, but most other countries, including the US, use DALYs. And so if you look from left to the right, you have your point of birth. You might then experience some ill health, and then you might die early. The QALY considers the clear bit. The DALY considers the shaded bit. So they are a related metric, but there is way more data for the DALY than there is the QALY. The DALY then enables you to sum the harm from years of life lived with disability and add it to the years of life lost. So in concept, it's very simple. And we use toxicological data and epidemiological data, which is gained from populations, measuring populations of people, in order to determine appropriate values for these. And what we can do is we can get a number that tells us the amount of harm that some hazard might cause us. So here we've got 3: alcoholism, smoking, and transport injuries. And you can see that clearly smoking at a population level across the world causes 2.6 times more harm than transport injuries. And alcoholism lies somewhere just above transport injuries. Remember these numbers. I'll be coming back to them again later to provide some context. Now, Max here, we were trying to work out the other day when we first sort of became aware of each other, because we're sort of a little bit apart in age, but and so we've become friends. I would like to think over the last decade or so, but I think actually it's this plot that got us really talking and thinking and planning. Max stood up at a conference in 2012 in Athens in Greece, and I could see immediately that this was a very, very important piece of work. And I'm going to tell you about it now. So it was done at the Lawrence Berkeley National Laboratories. They looked at 77 studies reporting indoor air contaminants in the US and other countries with similar lifestyles like the UK and Canada. They calculated the health impact from each of those contaminants. They looked at the concentrations, and the health impact was then quantified as a harm using the DALY metric. And I think originally they started off with just under 270 contaminants, but there's not a lot of data on all of those. So you're constrained by 1, what people measure in homes, and 2, what toxicological and epidemiological data there is on those contaminants. And that's still true today, as I'll go on to demonstrate. But he showed then, back in 2012, that PM2.5s, so that's all particles with a diameter of 2.5 microns and less, were the most harmful contaminant in homes by an order of magnitude. Now, I'm sure most of you know this, but I just want to clarify. We call this a whisker plot. The top and the bottom line shows where, roughly 95% of the data is, and the dot in the middle is an average. Okay. So, what it told me and really guided my work for about a decade was that probably we needed to start thinking about particulate matter more than any other contaminant first. Why waste your time with these when you can get a bigger change, bigger bang for your buck? Goodness only knows if that translates. If you were to focus on PM2.5 first. Secondhand smoke, you can get people to smoke outside. Radon, there are good treatments. We know how to deal with radon. Formaldehyde, yes, we should think about formaldehyde. Acrolein often comes from the same source as PMs. So PM is where we should focus our evidence on. We thought. And then we decided that it was time to reevaluate these studies and start to think about how we could use this process that Lawrence Berkeley Laboratories came up with to do a bigger study and to start to change standards. So we did 4 things at Nottingham with Gio Morantes, our Venezuelan colleague. The first is we used epidemiological and toxicological data to determine a new metric of harm. And that's called the harm intensity. And it has units of DALYs per unit concentration exposed to over a year. So I'll show you what that means in a moment. We then needed to evaluate the contaminant concentrations in homes in the global north. So anywhere from America to Chile to China, we considered in the study. And then to combine the two to work out which contaminants were the most harmful. And then rank them by those that cause the greatest harm. So Max has already shown you this, and yes, ethanol comes out top. We looked at 136 studies. We looked at 827 data sets. So it's not a true picture, it's only the start. We'd like to think in 10 years' time again, somebody else will do this again and develop it further. But this tells us the concentrations of different contaminants. And we're reduced down to now 45 contaminants, which is an increase on the 15 of the previous study that we have data for. Let me show you an area plot for the concentrations. The human eye really struggles with the logarithmic y-axis. So you can now see just how much of this area is taken up with ethanol and particulate matter. You see PM10, PM2.5, and then formaldehyde and nitrogen dioxide. Now, you'll be pleased to know I'm not going to talk you through the model. If you really want to know, I can let you have a paper, but I can reduce down what we did to a couple of very simple concepts. Here is the dose on the x-axis and response function on the y-axis, and it looks a bit like the solid curve. But at the concentrations we're looking at in buildings, we're on the linear part of it. So we don't have to worry about the non-linearity of this relationship. We can just take the linear bit, which means we can have a really simple equation, and I like simple equations. Most of my work is highly aggregated. I'm interested in populations. I'm not a big details person, so this suits my personality pretty well. And the harm then is the mean concentration, or the median, concentration you record over a period of time, ideally over 12 months, multiplied by this new harm intensity metric that we get from the epidemiological and toxicological data for each of the 45 contaminants. And if you simply multiply the concentration by that harm intensity, it gives us the harm caused. Now I've changed the order from the plot that Max gives you, so you can see now that the harm goes down and, the harm intensity decreases. And chromium-6 here matters quite a lot, and so do the 2 particulate matter harm intensities. If we multiply the concentrations that I showed you by the harm intensity number that I showed you, obtained from epidemiological and toxicological data, we get the total harm. And Max showed you this plot too. And particulate matter here matters quite a lot, and you can see then there's a long drop-off. The human eye, as I mentioned before, really struggles with this logarithmic scale, because every horizontal line is, as you move up, is 10 times more harmful. So I'll put it on a linear scale for you, and you can suddenly jumps out at you which contaminants matter the most. These don't, which is why Max doesn't like TVOC, and I totally agree with him. I don't like TVOC either. And those on the edge matter more. I'll put that into an area plot now, so you can start to see which ones matter even more. And we're down to 1, 2, 3, 4, 5, 6 contaminants really that we can worry about. and should worry about. Now the question is, well, I've just said we should worry about, but should we? Should we worry about them? We know which are the most harmful, but does that matter? Should we be worried? Well, I would say very much we should be worried. If you add up the harm from all of these, because the DALI metric is nice and straightforward, you can add up the harms from each of the contaminants to get a total value. It comes to 2,200 disability adjusted life years per 10 to the 5 people per year. And if we go back to our numbers for other common hazards, you can see that it matters, right? It's not as bad as smoking, it's approaching smoking, but definitely more harmful than suicides and, alcoholism and transport injuries. Now, in the UK, there's not a big call to improve transport injuries or to reduce transport injuries, but there definitely is still ongoing policy to reduce smoking population-wide. And if there's a call to do that, we should probably be looking at our indoor air quality as well. It matters. It matters very much. Building tight, ventilating right, matters. So PM 2.5 on its own is a significant proportion of that harm, and is where we should really think about our efforts to try and reduce this contaminant to make us all safer. So let's go back to the harm from the WHO threshold values. If they were doing this the right way, the harm from each of these threshold values should be the same, right? Why would they be different? If I now use the harm value for PM 2.5 and say that we're going to allow the same harm from nitrogen dioxide and ozone, what happens to the concentrations? Do you think they're going to go up or go down? Well, the PM is going to be the same, obviously. But actually, they are over-regulating nitrogen dioxide and ozone relative to PM 2.5. Now, we would also argue that this isn't a particularly good way of regulating these contaminants either. And you'll note that this isn't the way that's just going to go into standard 62.2. And Max talked about the concept of a harm budget. Now, interestingly, the WHO used the concept of a harm budget in other areas of its work. They use it in drinking water. And the WHO has a tolerable disease burden of 10 to the minus 6 DALIs per person per year for drinking water, which is pretty tiny, actually, relative to the things we're looking at here. Actually, I've been using mine, ours as we've been giving our DALIs as per 10 to the 5 population per year. It works out at 1 DALI per 10 to the 5 people per year for drinking water. So using the same units is always the right thing to do. So how do we set maybe a limit of harm akin to the way that the WHO has done for drinking water? One way is to use what's called a reference scenario. Now, one of Max's former colleagues at the Lawrence Berkeley Lab, Brett Singer, has looked at a sample of homes in California, 70 of them. It's not a huge sample, I acknowledge. This is a good starting point, though. It's the best we've got. We need to do better. And all of these homes comply with the California Energy Code, which means that they comply with ASHRAE standard 62.2. Now, in those homes, they measured PM 2.5, formaldehyde, which is the HCHO, and nitrogen dioxide. So we have concentrations of the contaminants in there. They didn't measure radon and ozone, so what we used is guideline values for those. And if you calculate the harm from the measured and the guideline values, it gives a total harm for these homes of only 610 DALIs per 10 to the 5 people per year, substantially less than what we expect in most homes. So maybe this could become our reference scenario from which we start. We go from here. And this formed the basis of the numbers that Max showed you earlier on. So let's compare that then to the other harms for these hazards here. And what we find is if we can get all homes to meet ASHRAE standard 62.2, we're going to have a significant reduction in population harm. And that's good for everybody. It's good for governments, it's good for future economic growth, it's good for families, etc. What about other buildings, I hear you say? We've just done homes. Geo has been working to look at offices, and you can see here too that the same sorts of contaminants are appearing in offices as well. And that's good news, actually. It makes, for consistency, it makes things much easier. Where else could we think about using DALIs? Now, Max and I have had a few discussions about this plot, and neither of us are very comfortable with all of the numbers in it. People are starting to quantify the harm caused by the recent pandemic, and you can see some numbers here of DALIs. Now, I've put them up as DALIs per 10 to the 5 people per year. Actually, it's not quite the same units. It's not applied over a year. It's applied over the pandemic. So I am comparing apples with oranges here. Nevertheless, with the right work and a bit of time, we could get numbers where we could then say, well, do certain airborne pathogens matter as much as, say, PM 2.5, formaldehyde, ozone, etc.? In this form, this plot is quite controversial because what it purports to say is that COVID is much less of a risk than indoor air contaminants, and I'm not saying that at all, by the way, just so I'm clear on that. Maybe we could use DALIs to think about other areas or other factors that affect indoor environment quality, not just air quality. So what about our audio quality? What about our visual quality? There are DALI numbers for blindness. There are DALI numbers for deafness. Maybe we could use some relationship to work out how the potential harm could be in a poorly lit space or a space where we struggle to hear those who are speaking in it. I think this is entirely possible. Okay, a slight change of tack. How do we now mitigate against exposure to some of the contaminants that we're thinking about, and pathogens for that matter? There are a number of new technologies emerging that people are becoming increasingly interested in. Ventilation, yes, 40 years of study, we're still trying to work out how to ventilate properly, but we have a good start on that. Filtration. I'm sure many of you who work in practice are installing and being asked to install various grades of filters into your systems, both in line and maybe in the rooms themselves. Ultraviolet germicidal irradiation is another one. During the pandemic, we were asked to reduce occupancy. Now, if you maintain your airflow and reduce your occupancy, your airflow per person goes up, right? Now, all of these are essentially a way of providing clean air, or increasing the clean air per person, but without actually having to provide additional outdoor air. And so we call them ventilation equivalents. And the ventilation equivalents, I'm going to read the definition. It's the equivalent clean air flow requirement for a space or system. I'm sorry, I've just lost it. Where did it go? Yeah. It's the flow rate of a contaminant or pathogen-free air that, if distributed uniformly within the breathing zone, would have the same effect on contaminant or infectious aerosol concentrations as the sum of actual outdoor airflow, filtered airflow, and inactivation of contaminants or infectious aerosols. Okay? Now, This concept has already been employed by ASHRAE. It's in Standard 241. For those of you who've read it, if you haven't, it's right there on the table. You can start working through it after this session. But its purpose was to control infectious aerosols and reduce the risk of disease transmission in occupiable spaces, focusing solely on long-range transmission. And I was lucky enough to work on that. I did the modeling that underpinned some of the numbers that are in there. One of the things it does, or the numbers that it gives, are not outdoor airflow rates, but equivalent clean air flow rates to mitigate against infection risk. Now, a prerequisite of meeting Standard 241 is that you meet Standard 62.1, Standard 62.2, or for healthcare, 170. And when Max comes back to finish his talk next time, he can bring 170 with him so you can read that too. But these standards are the minimums. We can't even hope to get to 241 unless we're meeting 62.2, 62.1 and 170. And don't worry, there are many other countries who don't meet them either. One of the issues is we don't really know our buildings very well. And I mean the whole world here, not a Chile problem, international problem. We don't really know whether our systems conform to code. What systems do we have? How are they controlled? What modes do they operate in? Do they actually work? Are they documented? What is the maximum airflow rate that they're capable of delivering? Now, Standard 241 then asks you to go from a standard normal operating mode into an infection risk management mode. It doesn't say when you should go into that. That's set by cognizant authorities, maybe the building owners, maybe government. And that asks you to think about these things. Everything from air cleaning to operation and maintenance. But the key thing is the building readiness plan. And it looks a bit like that. That's an example table of contents that comes from Standard 241 and really asks us to know our buildings so that when the next pandemic comes, where the threat is airborne pathogens, and it's very likely that it will, we are ready. And we can only do that by knowing what we've got and how to use it, and by training people well. And that was something that Constanza was calling for in her talk. And so I tie it back to the beginning and we'll bring an end to my talk now. There's a number of quick summary points here. I won't read through them. I think just to summarize, the harm-based approach to indoor air quality is the future. We can now think about how to mitigate against many of those contaminants by using not just outdoor air, but by using equivalent clean air. And if you remember the plot that Constanza showed, which showed a decreasing concentration line with a linear energy line with some intersection on there, we can do this now for a whole lot less energy by using some of these new technologies. Preparedness for the next pandemic requires planning. Planning requires knowledge of what we have and how it works. We need to plan. Thank you very much for listening to me.
Bien, espero que nos hayamos dado cuenta lo importante que es traer a los expertos que están detrás de todos estos trabajos y esfuerzos para que nos hablen en lo que deberíamos hacer como industria y como academia. Bien, los invito, vamos a recortar un poco el tiempo, tenemos que evacuar el auditorio a la 1, así que tenemos 15 minutos de una ronda de preguntas. A quienes quieran hacerlo en voz alta, vamos a tener la traducción para los expositores. Si lo quieren hacer en inglés, también mucho mejor. Bien, los invito. Muy bien. ¿Quién quiere romper el hielo? Alguien de la industria quizás que quiera hacer alguna pregunta. Dale.
Gracias, Alejandro Rodas por acá, Chile Chapter, ASHRAE. Entendí, esta es una pregunta para Max, pero también está abierta para Valerie y Ben. Entendí que había una correlación entre el CO2, el CO2 y mental illness, problemas mentales.
No, I'm sorry. That was a bit of a joke. I meant to say that people who were worried about CO2 had some mental illness.
Maybe just to fill in on this, what have been shown is that in some study, not all of them, there is a correlation between the CO2 level and the ability of child to learn at school, basically, their capacity to learn. This correlation has been shown in some study, not shown in other studies. So, well, we're not quite sure what we've got here. And also, there is absolutely no causality that has been proved. It means that when they use some bottle of CO2 to emit the CO2 instead of human being, then you can see no impact of the CO2 level on the ability to learn in school. So if there is a link, it's only a correlation, it's not a causality. So that means that the CO2 would be able to detect that something is emitted by human being in a room that has an impact on the ability to learn. And this is also subject to debate, as I said, but it's not, this is for sure the CO2 itself, well, unless you go above 50,000 ppm or whatever, that has an impact on the ability to learn and the ability to sleep.
Hola, Daniela Méndez por acá. Quería saber cómo se miden los otros aspectos que no son CO2 en la calidad de las viviendas residenciales hoy en día. Porque nosotros CO2 lo medimos con los jobos, etcétera, pero lo demás yo desconozco y no sé si eso se mide y si es importante medirlo como para hacer políticas públicas o algo así.
So
Any of you can respond. Yeah, go on.
Well, it's true that CO2 is one of the easiest things to measure. So measuring it is not the problem, but what it means is the problem. And so, as Ben and I said, particles are probably the thing that affects the health the most inside. Measuring CO2 is not going to help tell you what the particle level is. You can, in fact, particles may be the second easiest thing to measure. So you could measure them, but in a practical sense, you don't have to measure them. You can just get rid of them with filters if you have a system that works that way, and then you don't have to worry about it. If you are doing forensic research, if you're trying to figure out a particular house that has a problem, then you may have to do some much more difficult things. But for an ordinary house, you don't need to measure these things. You just need to have good ventilation and good filtration, and you're done.
Yeah, if you only focus on health, clearly CO2 is not the thing to measure. CO2 will have an impact on your comfort. Well, CO2 is correlated, again, it's correlation, not impact directly, on your comfort, on your well-being in the houses. If you don't want to that it smells bad because of other occupants that sticks, or if you don't want to when you wake up in the morning that your bedroom feels fresh, basically, you need to have a ventilation flow rate that is appropriate compared to the number of persons that is in the bedroom or in the apartment. And CO2 is very good for that, to say, okay, the ventilation flow rate is well correlated, well appropriate compared to the number of persons in it to keep the room comfortable, I would say.
And it's mostly below roughly 1600 ppm for that comfort purpose, which for most standards, at least if the air is well mixed, you're going to achieve that anyway. As I said, for ASHRAE, it's normally about 1,000 ppm.
If it's well implemented.
If it's well implemented, of course.
Yeah, I'd like to talk about the systems that you might use to remove PM. So in the home, the primary sources come from smoking and combustion and from cooking.
You should not smoke, you should not burn things, but you should cook in your home, right?
You should cook in your home, absolutely. The PM is emitted when we brown food, when it turns brown, the Maillard reaction, the thing that makes it tasty and yummy, right? You know, a steak without a brown crust on it isn't worth eating. So, unfortunately, the thing that makes our food taste good is also not so good for us. The way to deal with that is to have a good cooker hood that is on while you're cooking and for a period of time afterwards as well. A period of time of 10 minutes will work terrifically well, we think. And that cooker hood must extract to outside. It mustn't be one of these recirculating cooker hoods. You know, that's not ventilation. This is... And I don't think this is one of those situations where air cleaning is going to work because there's all the grease in the air is going to get trapped and clogged up in the... So that's a simple regulatory change you can make to have a significant impact on population harm, and the cost, of course, is outsourced to the homeowner.
If you change a filter every 2 weeks, it will work, but who will do that?
No. Oh, for other environments, sorry, beg your pardon. For other environments, then the source is, like offices, is very unlikely to be those things I mentioned. So it's probably coming in from outside, in which case you're going to need inline filtration through your mechanical ventilation system.
Hola, Valterio Osorio de ASHRAE Chile Chapter. La consulta es si hoy día estamos saliendo un poco de la mítica del CO2 y hoy día con los otros componentes que están de alguna manera afectando la calidad del aire, como el formaldehído o el radón, la única forma de la dilución, más allá de la ventilación natural, ¿tenemos que hacerlo vía ventilación mecánica o hay otros dispositivos, otras cosas que podrían funcionar para mejorar la calidad de aire interior? Ejemplo, UVC o otros tipos de sistemas de purificación, ya sea con filtración. Eso, gracias.
¿Qué es UVC? ¿Qué es UVC?
UVC.
Oh, okay.
So I think the answer is kind of what Ben and I were talking about. You can get by with a lower outdoor air ventilation rate because to, let's say, 3.5 liters per second per person or something of that order, if you take care of the other contaminants of concern. Particles are one, and we know how to filter those. And NO2 is a product of combustion, and if you've handled your combustion appliances correctly, you might not have a problem there. Formaldehyde is the next most important one, and that can be handled if you make sure the building materials don't emit much formaldehyde. So if you do all that, it's fine. In terms of UVC, normally it's not important to use UVC because we don't have that many pathogens in the air. Now, in an epidemic situation, it could be COVID, it could be the flu, that may be an alternative thing, but for most respiratory pathogens, filtering works very well. So if you have a good filter running all the time, you're also giving yourself protection against those pathogens.
If we may add, the space station is able to work without outdoor air. So if the question is it possible to have people living in place where there is no ventilation with outdoor air, I say, well, it works in the space station. I don't know for Chile, but I know that for European buildings, the quality of construction is kind of below the quality of the construction of the space station. It's also cost a bit less. And worst of it, we do not control what we bring in the building as we control what we bring in the space station. I mean, they usually do not go to IKEA in the weekends to buy a new furniture and set it up in the space station, while people do in their house. They usually do not burn the steak also in the space station. It's quite disgusting, actually, what they have for lunch. Yeah, not grill the steak, sorry. So you cannot get rid of the total ventilation. Everything's work together. Source control, ventilation, and in addition, air cleaning will help. But removing totally ventilation is difficult for without knowledge right now. You can reduce it. Removing it totally is kind of, in my view, impossible. And with those kind of air cleaner, you've got to be very careful of the byproducts that are produced by air cleaner. If it's just a HEPA filter with a fan, it's fine, you're right. But you may have ozone produced also, and there are standards under development on this subject. So be very careful with the kind of system. All air cleaners are not the same, and all are not safe.
Yeah. And also, it's very expensive in the submarines and space stations to provide the air. It would never be a practical solution on the ground. And following on, UVC can produce a lot of byproducts when it hits materials. And this is only beginning to be studied now. So it's something to be very careful of. And I don't usually recommend UVC outside of some sort of healthcare environment where it might be important.
¿Aló? Rodrigo Pino, soy ingeniero civil. Agradecerle a los tres expositores, me parece muy clara su exposición. No es fácil hacer alguna pregunta muy inteligente porque prácticamente los tres expositores mostraron muy claramente el tema y cuáles son efectivamente aquellos elementos que más preocupan en la calidad del aire interior. Así que más que una pregunta es consultar si además de las tradicionales formas de reducir estos elementos a través de los filtros, a través de ¿cómo se llama? Todos los sistemas que ustedes manifestaron, hay estudios que, dado que la mayoría de estos elementos son gases, supongo, no se ha estudiado la forma de que con algún otro gas que sea inofensivo al ser humano se logre desplazar o confinar estos elementos para que sea más fácil su eliminación o su reducción a través de los mismos sistemas mecánicos o forzados, ¿no?, o naturales. ¿Se entiende la pregunta?
Gas
claro.
para...
Hay, como innovación tecnológica, no hay estudios que busquen a través de algún otro gas que sea inerte al ser humano el desplazar estos otros como el radón, el dióxido de nitrógeno, etcétera, digamos, que ustedes manifestaron como elementos que uno quisiera que no estén presentes en el interior de las viviendas para que sean desplazados. Hay gases que pueden desplazar a otros gases o confinarlos en la altura para que sea más fácil después su extracción. ¿No hay estudios conducentes a eso o a revisar si es posible eso?
Correct.
So we do have gaseous air cleaners that can remove gases, but in terms of adding something that's going to remove it, it doesn't work for two reasons. First of all, the amount of the bad stuff that you have in the air is very small. It's very distributed. It's only a few parts per million of what's ever in there, which means the thing that you're going to put in is also got to find these little things to capture them. And second of all, and more importantly, the thing that you would put in would have to be much more reactive than what's there already. And it's almost certainly going to be bad for you. For example, ozone will clean a lot of things out of the air. It'll make it smell good. It'll remove all sorts of bad things. Unfortunately, it is far worse for you than any of the things that you're removing. So as a general rule, we say that in indoor air quality, there's nothing you can put in the air to make it better. You have to take things out of the air to make it better.
En términos de tecnologías, también se han creado algunas pinturas que dicen limpiar el aire. En realidad, la magnitud de esa limpieza no es sustancial, no crea mejoras sustanciales como para poder utilizarlas en gran escala. Y hay otros que dicen que las plantas también podrían limpiar el aire. En realidad tendríamos que vivir en una jungla para poder sentir la mejora. Creo que tenemos tiempo para una pregunta, dos preguntas rápidas y termino.
Yeah. Third, thank you very much for your presentation. I have two questions. A short one, what would be the impact of installing a range hood in the kitchen on the air tightness of the building? And the second question is, as you probably know, in the south region of Chile, we have some cities with a very high level of pollution, outdoor pollution, due to the use of firewood, for cooking and heating. So, what would be your best recommendation to reduce the indoor PM2.5 concentration inside the houses, knowing that a big part of the outdoor pollution goes to inside by ventilation and infiltration?
The way we handle this, the second part here in the US, is we have recirculating air systems in the home. So we put the filters in there. It doesn't matter whether the PM was produced inside or outside, it gets cleaned out of the air. And that's the easiest solution. But when you don't have air distribution systems in the home, when you have a single extract and many inlets, you could only do the same by putting in room air cleaners, of which there are many products to do that. That's a bit of a last resort because it's not the cheapest way to do that. In terms of your first question, if you have too tight a space, a range hood will cause problems. You can fix that in a couple of ways. First of all is to get a range hood with a high capture efficiency so that you don't have to have too much air. You can also have extra openings that open when that. And an even better way, but much more expensive way, is they design range hoods where the makeup air is injected around the range hood, so it very much improves the capture and keeps the space at neutral.
Quite costly, but
there is an ASTM standard for testing range hoods, and it's just being revised at the moment, but that's going to be rolled out fairly soon and is being implemented. I don't know if it's being implemented in the US, but I know a number of European countries that are interested in using it, and manufacturers too.
It's in process.
And if you were talking about the value of air tightness of the building, I think that's what you are. When you've got a range hood, you need to have a clap that's closed when the range hood is not working, and then you test the building in depressurization so that the claps remain closed. That's one thing. That's a good thing with performance-based regulation. If you need to meet a certain level of performance, then you can get rid of that because you can take into account the flow due to the hood in the energy performance calculation. If you are prescriptive, then it's a bit more difficult because you don't know what to take into account, what is already taken, what is not already taken. So it will impact the air tightness of the building, that's for sure, just like the ventilation system itself creates hole in the building. But, I mean, that's the point of the ventilation. It will impact on the energy use, of course, but that's for the good things, to get a good indoor air quality. So it's all a matter of balance.
La última pregunta va relacionada a las dificultades que han tenido ustedes y es abierta lamentablemente a todos, para saber las dificultades que han tenido para poder acercar todos estos procesos de investigación al sector público y con eso transformar a un impacto que sea más transversal. Porque todo puede reflejar mucho desarrollo e investigación, que es el problema que tenemos como universidad, pero ¿nos podrían comentar cuáles han sido sus experiencias para resolver o qué barreras han logrado resolver para nosotros también desde Chile poder impactar de mejor forma el beneficio a nivel público?
That's something Spain is always telling me. Why are you still working on airtightness? Everything has been found. I mean, what's the point of working on this subject? And my answer is yes, in terms of research, investigaciones, almost everything has been done. But not because the researcher know what is the right things to do, that the 200 countries in the world do implement it rightly yet. I mean, we've got, 5 countries in the world who get a requirement on airtightness, while we know for 30 years that this is the thing to do. So, indeed, we know how to do it. It needs to be done step by step. It needs to be implemented in standards. It needs to be included in the regulation. Step by step. We are not talking about something that costs a lot of money. We are talking about something that people need to realize it's important to change construction habits so that it's actually implemented. And the only way to do that is that it's included in standards and regulation. Not necessarily as a requirement, as I've shown the example of Belgium, is very important how just introducing it in the calculation have changed everything on the subject. And actually now it's almost a context between builder. Oh, I've made 0.6, what's your last number? 0.5, yes, record, win. I mean, this is a mind changer. It's not costly. That's what I want to really, it's really important. We are not talking about solutions that will double the price of your building. As long as you have an heating or a cooling system in a building, you need to think through for the comfort and for the indoor environment quality. So you need to implement those things, and it won't be very costly if it's taken into account from the very start of the design.
I've really struggled to get traction to persuade the right people to make change. In fact, my work is better received in the US than it is in the UK. I've had some minor changes to get cooker hoods differentiated from recirculating cooker hoods in UK building regulations. But the main way I've had traction is through third-party organizations like ASHRAE, CIBSE, AIVC, rather than with government itself, because when these organizations start to make the changes, eventually government has to listen. One of the problems is I think with our socialized healthcare system that we have in the UK, we could probably save that system a lot of money, but they don't like predictive models. So, you know, it's very difficult to show that some implementation could be used as a mitigation method as part of healthcare treatment. I'm still working on that. And when I find out how to do it, I'll let you know.
The building industry is one of the slowest moving industries there is worldwide, I think. It's not the high-tech Silicon Valley industry where it gets an idea and the next year you can buy one. It takes a very long time. People are set in their ways. They learned how to do something from their father or from their company. They still do it that way. They don't want to risk doing it the other way until they have to. So there are many things you have to do to get it. I mean, Valerie's still working on airtightness, where, as you know, we finished the research in the 80s. So it's not that anybody is dumb. It's that the industry takes a long time, and you have to get people involved. It doesn't work as well in the U.S. to use standards because we're kind of against that, or regulation, I should say, against forcing people. So we have to convince people. And yes, getting people to say, I did a 0.6 today is a good thing. Then it's competition. So it just takes time, and you have to keep plugging at it unless you have a strong enough arm to force it with regulation.
Yo quisiera solamente dar el punto de vista también de la academia. A nosotros también es un llamado a poder entregar las interpretaciones correctas de las investigaciones de forma de que sea clara cuál es el rol del sector público, por ejemplo, de establecer cuál es el límite o cuál es el nivel de aceptabilidad que se requiere. De ellos depende exigir el nivel de aceptabilidad. Y por el otro lado, el sector público, también me gustaría que de repente nos dieran un poco más de tiempo para poder llegar a contestar las consultas públicas cuando las normas estén en revisión. A veces dan muy poquito tiempo, uno no alcanza a entregar las observaciones que uno quisiera entregar y lamentablemente las normativas a veces terminan con algunas observaciones que no sé si será posible ahora poder corregir. Así es que yo creo que eso fue un mensaje muy personal, pero yo creo que igual refleja las perspectivas de todos nosotros. Así es que eso. ¿Alguien más quiere? Any other comment?
Hola, buenas. Mi consulta más que nada es para saber la opinión de ustedes en cuanto al tema de las filtraciones de aire y hermeticidad. Poniéndole mucho énfasis a esto, ¿ustedes creen que esto afecte tanto en el diseño de las viviendas como para hacer algo, una casa, diseño hermético, al punto de que se eliminen las ventanas como casas del futuro, volviendo un poco al diseño antiguo?
Gracias, Constanza. Voy a complementar esa con una pregunta que llegó del público, que está en línea. Dice, en Chile se utilizan aireadores en muro o ventanas, trickle vents in the UK. Además, en Chile las casas que tienen aparatos a gas, se requiere además a lo menos una cierta área de ventilación y la hermeticidad de nuestras viviendas no son buenas, tenemos muchas infiltraciones. La pregunta es entonces, ¿qué sentido tiene colocar aireadores pasivos sin controlar de buena forma la hermeticidad? ¿No será mejor una correcta ventilación operando ventanas? Creo que tiene un poco también una conexión con esas dos preguntas.
This is mine. Okay. Your question was, can we remove all the windows if we've got a ventilation system, basically?
Can we go back to the use of windows for ventilation?
Oh, sure. Of course you can. No problem. It would just cost you much more money and make much more uncomfortable building. Well, I mean, why are we going there to the ventilation system? It's because people want more and more comfort in their building. They want to maintain a certain temperature, and they want to not feel the draft of the air, the cold air coming on them. So the more comfort you've got, the more technology you've got to get in your building. I mean, you can live in a tent. If you don't have it in system, it will be zero energy, no problem. But, I mean, it's not very comfortable. And if we require comfort, we need, if we want this comfort not to be too costly, to have efficient system to renew the air. I mean, of course we can go back to windows opening, but what will it cause? It causes either that the windows remains open long enough so that you make sure that all the pollutants are removed, and this is a lot of energy waste, or you open the windows just 10 minutes in the morning, then close it all day, and it's exactly the equivalent as saying to someone, okay, you are allowed to brace 10 minutes between 8 and 8:15, and then you just all bracing for the rest of the day. It doesn't work like that because the pollutants are produced permanently, so you need to have a removal that is, if you want this to be energy efficient, perfectly in adequation with the pollutant production. So going back to windows is possible. It's just that if it's not automatically opening and closing, it won't be either energy efficient or provide a good indoor air quality.
Creo que ya estamos. Espero que haya satisfecho sus expectativas. Les pido un aplauso, por favor, a los tres invitados. Thank you very much for coming. Y los próximos que están quedándose con nosotros al workshop, los invitamos también a pasar a la Escuela de Construcción Civil. Aquí los vamos a guiar. Los que no estaban inscritos, yo creo que hay suficientes espacios también para que se queden a almorzar con nosotros y sigamos discutiendo sobre la ruta que debiésemos seguir como país. Así que muchas gracias y gracias por venir.